speak LSBU. So,
We're not, this is just practice.
You have to coordinate with Harry basically for like
who?
Harriet.
So carriers are so let's give Harrier a moment, and then we can actually do a rehearsal as it's going to. Because otherwise, it's all a bit pointless now. It's going to be great. Who's your odds-on favourite to win? Oh, sorry.
LSBU.
I haven't actually gone around, but I like the LSBU team. Yeah, they seem very.
You could say LSBU have got 2 teams racing today, but there's 11 races in total. 11 teams.
Excuse me, you know what? We get first up.
No, I don't. Sorry.
They're all like.
And you're on brand. We're all on brand. That's my LSBU. That's not us.
Sorry, do you know anything about that stuff?
Is the Wi-Fi working now? Yeah.
Yes. So. Have you seen the
Hello, welcome everyone. Welcome to the 2024 IMechE Design Challenge. My name is Abdul. I'll be providing commentary for today, as well as a few interviews throughout the day. Today we're at LSBU. We've basically brought forward 2 teams from our end. The judges are currently in the deliberating room, but they'll be ready to start the event by 10:20. Thank you.
Elisa around, I need to get into their room. Yeah, hard drive.
Join us at London South Bank University for the making of you.
because I'm talking to one of the Imperial teams, they said they... Oh, this is yeah, let's hope you can. Your device can only come back.
Sorry, no access here, please. And also tomorrow.
Can I do it another time? Can I do it once again? Yeah.
Okay, good morning, everyone. I'm Elisa Puccinelli, one of the lecturers for the Mechanical Engineering and Design courses here at LSBU, and the chair of the GLR Design IMechE Challenge. Welcome, I hope you have a good time. I'm going to pass on for our head judge, Captain Matt Lister, to give the formal welcome to everyone.
Lovely, thank you very much. Good morning, everybody. As Elisa just said, my name's Captain Matt Lister. I'm a naval officer. I'm a submariner. I specialised in what is called SSNs. The Navy calls them fleet submarines. Hollywood calls them hunter-killers. Take your choice. It's exactly like it looks in Hollywood as well. I'm an engineer. I'm what's called a marine engineer. That is power and propel. So we make the big spinny thing at the back spin round. We keep the captain's bunk light on. And for UK submarines, that means we're nuclear specialists. We're the ones who look after the nuclear reactor and all of the various systems that go hand in glove with that capability. As a young man, I worked in design. I was the tech lead for future propulsion systems for the next generation of submarines. Today, I run the safety engineering team within the Nuclear Design Authority for the Ministry of Defence. So what we do is we take all the new designs that are coming in from Rolls-Royce or anybody else who wants to bid for them, and we assess those and we approve those on behalf of the Ministry of Defence. We manage designs in service to make sure that they're still safe and that they're still operating good nuclear safety for the RN. And we manage those right the way through to disposal and ultimate defuel, so on and so forth. I explain my job to people, and to me it sounds really professional, it sounds spot on, and as a good engineer, people see this for some reason. I don't really understand why. Okay, that's me. I was a student. I loved being a student. I loved it so much I did it 3 times. I did an engineering degree at Southampton. I graduated from UCL. I've done a degree at KCL, and I've even got a postgraduate diploma from the University of Surrey. So I've had lots of time in higher education. I absolutely loved it. And it's all contributed to a sort of 20-year career in military engineering. So I'm a huge advocate of initiatives like the IMechE Design Challenge for exactly that reason. Enough about me. Who are you? Okay, some pop quizzes. See if you can guess any of the names that are flying up on the screen in front of you. Okay, this is who you are. These are design engineers. celebrated design engineers. Okay, and if I do this job for 20 years, it is my first year, just in case you hadn't spotted that, I want to be able to put some pictures of you up on these screens, because you are design engineers and that's what you're here for today. That's why you're studying and that's why you've taken on this challenge. In my view, the people that you see up on that screen, they're superheroes. You probably don't think of engineers like superheroes, but these people saved lives. They changed the world. They made nations, defended nations, safeguarded people. They are as close to superheroes as you get in today's modern world. And just like any superhero movie, there's a point at the start where they kind of discover they've got these superhuman powers of engineering design. That's right where you are. You're at that stage in your engineering career. And it's a really good thing that you are, because just like any other superhero movie, there is peril. There are things coming that want to end all life on Earth or change the world that you live in dramatically. Now, I don't know if you're watching the news, but politics is not sorting out these problems. Politics is putting up the police tape, it's keeping the crowds back, and it's waiting for science and engineering to get stuck into these problems and get them sorted out. And best we do, because some of them are really quite stark. If we don't deal with these issues, the world's going to be a very different place to live in 10 years' time. Now, I know that's a lot of responsibility to thrust on young shoulders, but you're superheroes. With great power comes great responsibility, so on and so forth. And just like any good superhero movie, the real thing is when the heroes learn that they're not on their own. And you aren't on your own. There are design engineers that are out there now, today, solving these problems. They just need you there with them. And that's what your degrees are about. That's what the engineering challenge is about. It's about helping you to develop an understanding of what your own potential is in engineering design, so that you can be part of this future in which we tackle these problems. So the IMechE challenge is basically superhero high school. It's about getting you to understand that you've got this power and this ability, and giving you a vision of yourself for the future. So please embrace it, enjoy it, and it's there to help develop you as the next generation of design engineers. Okay, always put a quote in a good presentation. It makes it look like you read stuff. Here's my favorite quote about engineering. Don't let the fact that I'm responsible for nuclear safety put you off, by the way. I was thinking of buying a house on the west coast of Scotland, maybe give it a few decades. Okay, I put this quote up because I think it's really good for you here. Engineers are fallible. You don't know everything. The worst engineers are the ones who think they know everything. Okay, the really good engineers are the ones who understand their own weaknesses, their own limitations, who face adversity and are prepared to fail and to learn from it. Okay, really important in terms of your approach. And that's equally as true here today. Your expectation, I have no doubt, is that your model is going to gloriously run up and down the track and is going to nail it and you're going to get perfect scores. Engineering rarely works out that way. The really good engineers are the ones who can face that adversity, adapt, keep going, and get to the other side. Okay, a word on engineering rules. I work in nuclear safety. I'm mostly a rule setter and a rule enforcer. Engineers have a slightly paradoxical relationship with rules. We get stuff wrong a lot, frequently. And when we do, it can be really horrific. One thing engineers are fabulous at, really good at, is figuring out why things have gone wrong. They're really good at that. Any of those incidents you can see up on the screen, I promise you there is a report somewhere that has worked out exactly what went wrong. It will have worked out what colour socks the technician was wearing when he tightened up the bolt that failed, that caused the leak, that caused the explosion, that caused the problem. We're really good at forensically analysing accidents and incidents. And what engineers then do is create rules. They write engineering standards. They create safe management systems. They establish regulators to stop these things from happening again. And the second they set those up, the first thing that happens is the rest of the engineering world challenges those rules and says it's over-regulation. It's not goals-based regulation. It's a system of rules that prevents us from doing what we like. It's red tape. So engineers have a slightly paradoxical relationship with rules and rule breaking. Here today, I want you to follow the rules. I want you to do that because this is a competition and we need to ensure fairness. Okay? But actually, what I really want you to do is learn an important lesson. The best engineers are the ones who can work inside a rule set intelligently, respecting the rules rather than challenging them. And I'm willing to acknowledge that some rules are very tempting to break, if for no other reason than it would have a great story behind it. Not here today, I'm afraid, okay? If nothing else, take away, I'm a rule maker. I'm a big respecter of the rules. Okay, final thought from me. Please try to have fun, okay? I know it's not fun like a foam party at the Students' Union, okay? It's professional fun. This can be rewarding. This can be exciting. It's an opportunity for you to really show off your flair and start to demonstrate those superpowers. I know writing a bomb isn't really that much fun. Trust me, scoring them is not a lot of fun either. But it's still professionally rewarding. And take it from me, after 20 years working in a very difficult domain, there are few things as satisfying as facing difficult challenges and beating them down. So enjoy it, show your flair and creativity. If you walk away with nothing else here, just remember you are part of the next generation of engineering design superheroes, and you need to unleash those powers in order to save the world of tomorrow. Thank you.
Thank you, Matt. I would like to call Ben Leishman, Dr. Ben Leishman, our Associate Dean of LSBU, School of Engineering.
Hello, everybody. Lovely to see you all. And I would like to do three things. The first is to welcome you all to LSBU. It's really a delight to be hosting this competition here. The very first thing I did when I became a lecturer was I went to UCL to watch a repeatable vehicle competition the day after I started. That was in 2016. And so it feels, you know, on a personal level, it's quite nice full circle to be hosting the repeatable vehicle competition here at LSBU. For those of you who have been to LSBU before, welcome back. And for those of you who haven't been before, welcome, and don't be strangers in the future. One of the great things about this competition is it brings together all the London universities, mechanical engineering and design, and I really think that's a huge positive. So come see us anytime, talk to our students, talk to our staff, work with us, and we'll be delighted. The second thing I want to do is just to say thank you to everyone who has put in work to make today happen. That's obviously incredibly important. I think it's one of those things where there are too many people to thank, so I would like to thank just one person, and that's Elisa. Thank you so much, Elisa, for all your work today. It takes months to make everything go smoothly in the way that it has, so that's brilliant. And then the third thing I'd like to do is just to quickly say congratulations to everyone who's competing here. I was watching the London Marathon yesterday, and they were showing the men's wheelchair race. The guy who won, I think, is Swiss. He's called Marcel Hug. And the commentators were saying he'd had a crash the week before, something had broken, and they had 3D printed a new part for his gloves so he could drive his wheelchair as efficiently as he needed to. And they were talking about it as though it was some kind of magic or sorcery. The idea that you could 3D print something in a week and have it ready for the race seemed astonishing to them. Everyone in this room has done that over the last week. And I think sometimes we can underestimate just how incredible it is, the things you can do right here to compete in this competition today. Most people who you meet out and around in London or anywhere in the world cannot do the things that you can do. So hold on to that. This is why university is a wonderful thing, I think, and why we're all so delighted to be here today, because you're doing amazing things. So that's really, for me, the most important of all the messages. And thank you all for being here today. Looking forward to the competition itself. Brilliant.
That's me again. So before I do some housekeeping about the event and to explain you how we're going to run the event, I just would like to say a big thank you for those who have volunteered to be the lane judges today. So Martin Robson, yes, just would like to say thank you. So he's the chair of the IMechE GLR Council. Also Charlie in the back. Charlie is also a member of the IMechE GLR Council. Also Tom Peach from UCL. Professor Steve Dunn from LSBU. Okay, so just a bit of housekeeping, some notes. We don't have any fire drill alarms scheduled for today, but in case if we hear any, we can just go straight to those corridors here towards the entrance, and then the security, they have been briefed, and they will take us securely to the evacuation exits. And how are we going to run this competition today? The first element is the presentation, so I will call the top 3 teams here to give the presentation live for you. It will be followed by the design review, which is the top 3 CAD models, are going to be presented here. The CAD models are going to be projected here and will be followed by some questions from our head judge. And then we'll break for lunch. And during the lunch break, we'll be doing 2 things, The students are going to be, the scrutinizing of their devices are going to happen during that, during this event. So it's during this part. So it's very important that at least 1 team member will be at the tables to answer any questions that may come up with the judges, The other thing, after your device is ready to go with the IMechE sticker on that, you can go around and do the peer review. So we'll give you some paper slips for you to choose which one do you think is the best, device. And then after that, we will start our challenge competition, which is the moment we are really looking for, So each device controller from each team will be into a lane, to run. So only one device controller and 1 judge per lane, And then we'll follow by the grand final. So the finalists are going to be compete head-to-head on the grand final, and then the prize giving, the moment we are also waiting for, and then the closing remarks by our head judge, Captain Matt Lister. And also to suit up the moods, we also have some refreshments, some snacks, beer and wine for you at the catering, And I hope you enjoy your day. And that's all what I wanted to say. And we will start now with the presentation from the top 3 teams. Can I have here the first team to present with steel shafters, please?
Hey, we are the steel shafters from Imperial, and this is our design process. So the aim of the competition this year was to build a repeatable vehicle that moves towards a wall and then returns to the target, the exact starting position. So with no programmable circuitry, a low budget, and 2 minutes to complete a run up to 4 meters.
Our initial ideas use a binary counter and an optical encoder to record increments of wheel rotations. But after clarification of the rules, we tried a gear mechanical locking mechanism. Accuracy was limited by the gear pitch, which turned out to be significant. So we then moved on to a thread rod mechanism with a nut moving up and down the thread to record distance and stalling the motor by mechanically locking it. However, this is bad practice, and the static friction of the mechanically locked nut was too great to overcome and start the car again. So, for our final design, a limit switch and a lead screw were used to overcome these issues.
The start button engages the logic to start the car, driving the car forward, whilst the rotation of the axle drives the lead screw along the thread. When the car hits the wall, the limit switch is actuated, braking the motor momentarily before it starts reversing. The lead screw is then driven back along the thread until it actuates the second limit switch, resetting the whole circuit. The process can be repeated by pressing the start button again, and a reset button is present for emergency stops.
For motor reversing, we chose a half bridge over a DP/DT switch, as it offers built-in braking and better electronic compatibility with alternative lower force actuators. Despite the more extensive circuitry required, analog components are cheap and enables us to avoid the bad practice of shorting or stalling the motor to stop the car, as done with simpler DP/DT switch circuits. So we decided to use a non-latching limit switches due to its low force actuation from its flexible lever design, which also damps the collision with the wall, as seen in the GIF.
Hence, the electronics uses SR latches made using non-memory logic gate components to latch the limit switch actuations, which holds analog inputs to the H-bridge, as seen in this MATLAB simulation of the initial binary counter design, where limit switches are modeled as buttons. For the thread rod variation, the first design is simplified to 2 latches, and finally for the lead screw variation, an AND gate was added to reset all the latches, which stops the motor when the lead screw limit switch is actuated. And here's a diagram of 2 SR latches that we assembled using 1 quad NOR gate.
For each circuit variation, we created a breadboard simulation on Tinkercad to ensure that assembled circuits are safe and functional, while using it as a reference for building prototype boards. Then we transferred into a permanent matrix board solution before designing a PCB for ease of manufacturing and lower cost.
The PCB, designed on Easy EDA, was smaller than the matrix board and turned out to be more reliable as the solder connections were easier. During the design of the PCB, we kept the signal traces on the top layer to use the bottom layer as a ground plane. During prototyping, we used gears to transmit power to the driven axle. However, poor quality output shafts caused misalignment and excessive friction. The use of gears also limited our choice in motor placement. We now use a pulley system with an O-ring functioning as a belt due to their high friction and low cost. Belt slip was not an issue as the distance was being measured by the physical mechanism on the shaft rather than the rotation out of the motor.
The chassis is designed to be manufactured by laser cutter to facilitate rapid prototyping. We opted for acrylic as the chassis material due to its lightweight properties and ability to absorb vibrations.
Finite element analysis on each chassis iteration gave us the insight required to minimize the surface area used and ensure that no excessive stress concentrations were present, reducing costs.
During testing, the data pointer always landed slightly to the side of the target. Upon inspection, we found out when the car drifts, the limit switch makes contact with the wall at an angle, resulting in a torque that causes the car to rotate slightly, as shown in the diagram. Consequently, the car does not follow the same path back, and therefore lands off target. To address this problem, we decided to minimize drift by using O-rings over rubber bands for traction. We used ball bearings over bush bearings to eliminate axial play, and we made the back axle mount adjustable with a slit in the chassis as shown.
So we aim to keep to produce the optimal design for the given budget. So most of our budget is attributed to the wheel assemblies, as this is where we observed the most performance loss in testing. The mechanical structure cost was kept low by 3D printing or laser cutting all parts where possible. And finally, we kept the fasteners below the 20p threshold. So our final IMechE total was £37.90 with a total cost of £39.72. But for further improvement, we would have liked to have used surface mount electronics and used the money saved to machine shoulders for the lead screw to aid assembly and precision. And then finally, this is our first perfect 4-meter run. Thank you for listening, and any questions?
Thank you. Oh, thank you very much. As I mentioned, I really like your idea of creating a logic electronic circuit. I have 2 questions about you. First, which year of university are you from?
We're all first year.
First, thank you. Second one, how did you deal with the backlash? So when you start your device and then when it comes back and press the switch, how do you deal with the delta in millimeter to get almost, or to aim almost to be on the 10?
So by using a lead screw with a 4mm pitch, this already reduces any backlash error. But when we start the car and do the actual run, we do one run beforehand, just a couple of centimeters, and click the limit switch, just so that it's exactly the same setup as it would be for the actual run. And the momentum of the car pushes the limit switch almost all the way along the shaft to actuate the limit switch.
Thank you. Great presentation. Really liked your use of media in the slides. And you gave a really good narrative of how your design had evolved. One of the things that customers look for when they're being asked to invest in designs, particularly big, expensive designs, is optioneering, evidence of optioneering. What options did you consider? Which ones did you discount? And why did you discount them? That becomes really important in terms of demonstrating the robustness of your option that you took forward. So to a certain degree, what a customer is really interested in is what did you discard and why did you discard it? So my question is, what options did you consider when you were drawing up your design? And when you were considering different options, what do you think the most important characteristic traits were?
So obviously the main consideration is the distance measuring mechanism. So initially we thought the most accurate method would be to use a binary counter and an optical encoder, which would be accurate to less than a millimeter. But clarification with the rules and some sort of like unsureness on what a memory component counted as meant that we discarded that. We then had a couple of ideas to mechanically measure the distance. So the 3 that we considered mainly were a gear counting mechanism, a threaded rod, and a lead screw. We tested all 3, and the gear counting had the most backlash as the gears were, the pitch between the gears caused the backlash. The threaded rod, due to not being a precision part, had quite a lot of backlash, and the lead screw, as they're used in CNC devices and 3D printers, were machined to a much higher tolerance and precision, therefore had the least backlash. And well, when we tested all 3 cars, it was the most accurate. So it was a lot of physical testing. And the sort of second consideration mechanically was the wheels. During testing, we had a lot of problems with wheels causing misalignment, as we were using laser cut wheels. So we tested buying in wheels, we tested 3D printing wheels, and we tested 3D printed wheels with a sort of tire around the outside using an O-ring, and that was what we went with our final design. And then some electronic considerations.
Yeah, and in terms of the electronics considerations, so we decided to use, of course, we made a breadboard first with some components. And we decided to use logic gates because all of these switches, so these are all very standard produced. So you can get any of these gates for 60p, for example. They're very, very cheap. And also that's why I want to move on to surface mounts, where each of them are about 5p. So we can build entire electronics a lot cheaper. And also, we decided to use an H bridge here, which is primarily because it breaks the car. Because when the car hits the wall, that causes a lot of error, the bounce and so on. But the H bridge allows us to swap the current so quickly, and basically it acts as an electronic brake. Because we also consider options for a mechanical brake, which is, first of all, extremely expensive and have practical issues in terms of manufacturing, tolerances, and so on. This is just a component that's cheap, widely manufactured, to solve our problems. And in terms of manufacturing, we found that breadboards are not very reliable because the wires can come off. And also, it's not ideal because the breadboard is expensive. So we went on to a matrix board. But of course, then again, matrix boards, they're cheap, but it's really hard to solder considering how many connections we have and to ensure there's no jumps in voltage and so on. So then we moved on to PCB, which also had a really high safety factor of 3.3. And also, it's really easy to manufacture. You just print it, and it costs £1, and you just solder it on the electronics. Nothing can really go wrong unless you solder it wrong. So it's all in terms of manufacturing and practicality as well.
Yeah, we also considered using a feather trigger, but we found that it didn't really match with the speed we were running the car. It was slow enough to the point where it didn't make much of a difference.
I think that's everything.
So now you explained that you did a couple of iterations or more on your wheels, and you discover later that friction was playing a big part in keeping the vehicle straight. You showed us as well there was a FEM analysis made on the chassis. Now, one of the things that we discussed or described in the webinars was start with thinking of the physics. So your vehicle will have a mass. The vehicle will have to transmit a vertical and a longitudinal force to be able to move forward and backward. And all these are the stuff that you could mature with your CAD and all the other stuff. I understand that you're the first year, and I don't want to give you hard times, but I saw that you were focused a lot in developing the electronic circuit, which I'm very, very happy to see. But I haven't seen that basic fundamental engineering say, right, I have a mass, I have a load, I have a friction. I need to understand that my wheel needs to develop a friction to move forward and backward, brake without slipping, move without finding. So suggestion or question, try to put more emphasis in presenting that you have been through the journey from the first principles, thinking about friction, thinking about efficiency, thinking about transmitting the force and the load, rather than jumping to some final decision. That may have helped you in already reducing some of your selection in some components at the beginning. So have you considered in your calculation some loads in a more engineering way?
Yeah, so initially we did some calculations to sort of work out the impulse of the car as it hits the wall, using an estimated velocity and mass of the car. And we kind of, a lot of it was empirical testing rather than calculations for the wheels and ensuring there was enough friction. We started with rubber bands on the outside of some laser cut wheels. And it seemed we didn't really have any issues with friction along the way. So we kind of felt that a lot of the main development needed to be in the electronics and the distance measuring system rather than the friction at the wheels and the alignment. But yeah, no, I definitely feel like we could have done some more, maybe some more calculations in reference to friction. But, yeah.
Thank you very much, Steel Shafters. I would like to invite now UCLA. Yeah.
We sit in order. Should we sit in order? Hi, we are UCL Team A, participating in the Foundation Challenge as a curricular activity. Our goal was to build a repeatable autonomous vehicle that travels to a wall and back up to 4 meters away and completes the challenge in under 2 minutes. It has to be a mechanical solution using analog circuitry principles only and must fit within a £40 cost cap. Our design philosophy was to use simple components which integrate seamlessly to build a robust and reliable vehicle. Our vehicle is fully adjustable and features an all-wheel drive system using a belt and uses a worm gear timing mechanism for distance measurement.
The alignment system is one of the most important parts of our car and has been changed a lot throughout testing, and it's based on three main components. Firstly, on both sides of the front axle, we have sliders, which allows us to induce an angle, which allows to reduce any lateral movement. Secondly, we have designed the DPDT bumper to be round, so even if the car hits the wall at a slight angle, at least it would go back at in the same direction. In addition, we have pre-tensioned the DPDT bumper with a rubber band, which allows it to reduce the impact forces needed to reduce any chance of disalignment while hitting the wall. Finally, we have a belt on the one side of the car to implement four-wheel drive, which reduces friction, improves the motion of the car, and reduces any chance of lateral movement.
The bill of materials is made up of 43 components. We have mechanical in blue, electrical in green, and fasteners in orange. These, combined with our industry-standard partnering system, is used in our CAD. The bill of materials was extremely important in our dynamic modeling because it gave us an approximate mass, which then allowed us to make friction calculations. It was also extremely important in our materials choices. As you can see, here are the fraction of the top three most expensive components of total cost and the relationship of the three sections of the BOM to each other. The bill of materials gave us financial restrictions on what we could use. We forfeited the use of aluminum wheels and only used one belt, thus making a cost-effective vehicle.
Okay. One of the main rules of the competition is for the car to travel the maximum distance, which is 8 meters, in under 2 minutes, and come back to the same exact point from which it started. We've gone through around 10 different design iterations. We've done sketches for them, some of which included a pullback mechanism, the rack and pinion solution, and a massive timing gear. However, we faced some problems, either technical or financial, with all of these designs, and we had to solve them to arrive at our final design of the vehicle. Our vehicle travels at a maximum speed of 0.084 meters per second, making the longest distance in 95 seconds. It fits the dimensions of the working envelope, being 396 millimeters long, 310 millimeters wide, and 53 millimeters high at all times.
So to measure the distance that the vehicle travels and return to the same point, we use a worm gear that has a 30-to-1 ratio with the timing disc. The timing disc captures the distance that the vehicle moves, and when it returns, it spins back to the same point, actuating a precise micro switch which physically turns off the motor and as well as locking the drive system, stopping it right on the mark.
Our circuit is powered by a 9-volt battery, chosen for its power density and high voltage compared to its weight. Using a DP-DT switch, we can introduce two separate circuits using one power source. We have a push-to-brake switch on the reverse direction of the circuit to stop the motor exactly on the mark every time. And using the DP-DT switch, we can reverse the polarity of the motor to drive it backwards once we've hit the wall. If you put the DP-DT switch in forwards, we can actually adjust the actuation point of the push-to-brake switch to ensure millimeter accuracy when we stop every single time. We also have a latching push-to-make switch before the DP-DT switch to act as a power button and an emergency stop, so we can fine-tune it even more.
So lastly, I'll be moving on to the baseplate design development. So our design philosophy for this was to reduce as much surface area as possible, so we reduced the amount of cost for the baseplate. So firstly, we have the original design on the left, which is our very first wooden design. Will be over on our table if you want to see it. And then I know it says acrylic there, but it was made out of wood. And then next we moved on to using shape optimization, which is identifying areas of low stress. So under that analysis, we identified spots we could cut out, and that ended up with the design on the right, and we reduced 35% of the the surface area. And next we move to a Voronoi sketch generator, which creates cells so that localized stress is minimized, but then we are still reducing the surface area which is used. So again, more reduction in surface area. And in order to prove this concept, we decided to use some FEA, and we used Fusion for this because we didn't have a professional ANSYS license at this time, and we are trying to get one. But so it shows the maximum of 15, but we assume that it's going to be a lot higher than that if we are able to escape Fusion. So this is moving forward. So we were not able to implement this because our workshop was closed at the time, but we did manage to manufacture it after the 1-week deadline that was last week. So we used generative design, so the load cases can be on the left, and we ended up with an average of around 65% surface area reduction from the very beginning. So this is after generative design, and we did try to prove this using further FEA, and as shown again, we're stuck with the maximum safety factor of 15 again, but we assume will be a lot higher. So this just proves our step moving forward if we are successful today.
Thank you. Any questions? Yeah.
Again, really good presentation. Love the way you balanced your slides out, and there was a nice structure and flow there, so thank you for that. Fantastic design engineering teams are very often undone by terrible customers. I am a terrible customer. I want you to take £5 off the budget for your concept. Can you still deliver the capability, and how would you do it?
It's a great question, and it's what we thought about. We're really close to the budget cap. What we would do, first of all, we would remove 2 of the 4 pulleys that we use. That would save about £2.5 in cost. By using the final shape optimized chassis, that would cut in half, basically, the price of our chassis. And we can also save money by making the wheels thinner, not actually the wheel that's in contact with the ground, but the hub of the wheel where it attaches to the axle. That is quite thick, and it could be reduced in size. That would save £5 in total. Yeah.
So I'm your second terrible customer here. So with my background in other field, sometimes you want to design a 95% of safety factor, so not 1, and check on the first execution that it breaks exactly where you predicted it break, to correlate if your calculations are telling the truth. And then eventually decided to have a safety factor of 1, 1.1, 1.2, 2, whatever it is. So go first, make it to break, check that it's breaking when you think it should, and then go with your safety factor. Now, following what Matt was asking for, safety factor of 15. I go by memory, but elevators go with safety factor of 12 minimum. I'm a customer. I don't want to buy something which has been over-engineered and it could be made cheaper. Did you got in mind any safety factor target? Because if you present a number, I want to understand why you have the number there.
I mean, so for the preset for this, actually for this generative design, we made the generative design before we even made the FEA for the original baseplate, so which is the one that's implemented, but not the one that's used. So we actually set the safety factor to 5. It ended up being the maximum of 15. But we thought 5 would be quite a good standard because 15 is over-engineering. And we do recognize this as a spot where we can save more cost. So looking forward, we can make the holes a bit bigger. So the Voronoi sketch generator, so the cells that we make for localized stress, so localized stress is minimized, so displaced. We could make these holes a lot bigger as there's more space. Obviously less holes, but there will be less surface area, so more surface area reduced. And that will probably take the safety factor down to maybe 8, but then honestly, there's not that much going on in this, and the safety factor will be high regardless, but 5 is what we aimed for, but we did end up over-engineering it, and it is what it is.
Yeah, I mean, we could have really used plywood, but as a customer, I thought, would I rather look at like a car that's made out of plywood or acrylic? Acrylic looks much better. And yes, it might be over-engineering. We didn't have the chance to change the Voronoi sketch generator, but in my opinion, in our opinion, the car looks better in acrylic rather than plywood. So that's another factor as a customer that I will look at.
Also, why we didn't go with plywood? Because initially we were meant to, but we've 3D cut probably like 2 or 3 base plates, and they all ended up being warped. So, which is why we went with acrylic, and it's a quite thick piece of acrylic. So, hence why we have such a high safety factor.
My customer answer that I would like to have heard from you about this. So plywood will be affected by temperature distortion and humidity distortion. So apart from the aesthetical appearance that is not in the requirement, so the rule of the competition have some requirements in it. Aesthetic is not there, and I'm sorry, and I'm feeling sorry for that one, but recyclability is not there. So the aim is to make a vehicle that goes straight. About your answer on the safety factor, it is if in your presentation next time you think about getting a target for the safety factor and then explaining that by manufacturing process you cannot go to the target and overall show the customer that they're saving money, even if they feel they're overspending, that will be the way where a customer could say, or Matt in this case would say, yes, you saved money enough to have a good product and a good manufacturing process without really trying to go to town for no benefit over there. So you could have done a journey. This is the mass, this is the cost, safety factor 20. My aim is to go to 5. This is where I go down there. If the cost doesn't move, I stop my iteration because there is no benefit. Just a recommendation for you to show that you've done a legwork in the background. And remember, aesthetic is not, so aesthetic, aerodynamics, or whatever are functional only if you think they are. In this particular activity, 2 minutes run and no requirement on aesthetic or on aerodynamic is up to you if you want to do something or not.
Can I add that for the FEA and the generative design that basically the most accurate material we could use is 6mm acrylic, and that plywood was not an option in whatever we went through, so maybe that adds to it.
It's not a question, I just wanted to say congratulations, I think you smashed it, and really well done guys. Acrylic or plywood or whatever, you've done a very good job.
Thank you, thank you.
Thank you, UCLA. Okay. I would like to call now UCLB, please.
Good morning, everyone. So, as many of you know, we're here to discuss the IMechE Challenge. The aim of the IMechE Challenge is to create a repeatable vehicle that can reach a certain distance to a wall before reversing and returning to a target position. And we're here today to give you a quick overview of our take on this challenge.
For us, success was reaching within a distance of 5 millimeters of the bullseye.
The run time should not exceed 2 minutes, and the setup time should not exceed 3 minutes. A single fuse must be installed with a maximum permitted current of 10 amps, and the distance between the data pointer and the ground should be 6 millimeters.
In the kinematics analysis, the vehicle's body is treated as a point mass because it's not rotating. Aerodynamic losses are negligible, friction between components is ignored, and all springs obey Hooke's law. Additionally, while electrical resistance was accounted for in the MATLAB circuit calculations, the numbers show that it doesn't affect the vehicle's motion.
As stated in the competition, it was important for us to create a CAD design that matched as accurately as possible to our actual physical vehicle. As you can see, here's a comparison between our CAD switch and the real DPD switch. It was important for us to create a vehicle that was as accurate as possible, not only for the points in the competition, but also to ensure that us or anyone could rebuild our vehicle from scratch with just the aid of this. Other important points that we included on the CAD include the milling of the front axle, well, partial milling of the front axle, to allow our pulley system to work properly, and the inclusion of individual 3D printed holders for all the electrical components to allow them to be attached safely.
We decided to use a pulley system instead of gears, as this is more reliable. 3D printed gears may have small misprints, which would lead to the teeth jamming. We calculated that we require a gear ratio of 1 to 5, so to accommodate for the larger pulley, we made a cutout in the plywood body, as you can see in the middle there. We added rubber bands to the wheels to prevent the wheels from slipping against the ground, and we aimed to make the wheels lighter through their design with these cutouts.
The gear ratio of 1 to 5 was required to increase the torque provided to the wheels to reach our target velocity of 0.1759 meters per second in 0.3 seconds, given the specifications of our motor. Our initial maximum acceleration is 0.622 Gs using MATLAB, at which point our vehicle does not slip.
To calculate the deceleration of the vehicle before it hits the wall, we used Newton's second law to create a differential equation which included the driving force of the motor as well as the force exerted by the spring inside of the DPDT switch. Solving this equation in MATLAB, we found that the maximum deceleration was around 0.16 Gs, at which point our vehicle does not slip.
In our vehicle, we have lots of different components that have to be connected in an entire circuit. We have an on-off switch, 2 AA batteries that give us a total voltage of 3 volts, a DPDT switch, a normally closed switch to stop the vehicle, a motor, a 3-volt motor, a 2-amp fuse, and we also have 5 1-ohm resistors that will explain why we have them later on.
To reverse the direction of the vehicle, we used a DPDT switch. When the DPDT switch hits the wall, it reverses the polarity of the current in the circuit, which causes the motor to turn backwards and the car to reverse. And the two circuits can be seen in the circuit diagrams on the presentation.
After the initial circuit design, we calculated the current which was drawn by each of the components in the circuit to determine whether the motor received enough and whether the fuse would blow. By using a combination of Ohm's law and iteration in MATLAB to find an approximating function for the resistance of the fuse, we then plotted the current in the circuit against the operational power of the motor and found that we would need at least 1 ohm of added resistance in the circuit to ensure the current was a safe amount.
To ensure our vehicle stopped at the correct distance, we've used a lead screw and a flange nut. The turning of the axle moves the lead screw along it so that when it then travels backwards, it will move back by the exact same direction before hitting a contact switch and cutting the circuit and stopping the car.
There were a couple variations that we did to the actual design when we were actually building it. For one, were the wheels. First off, we changed the version from 1 to 2 on the actual shape of the wheels. We decided to do that because it was going to be a bit more resistant to forces, and we didn't want it to crumble on itself like it did in version 1. We wanted to 3D print it, but that ended up being too expensive. We then tried to do acrylic, but that warped due to the high temperatures of the laser cutter, and we then ended up doing the wheels in plywood. We ended up laser cutting it. We then also added a rubber band, as mentioned previously. We then also added a rubber band on the DPDT switch, so when it actually hits the wall, it actually clicks it every time. because we were having trouble with it actually activating. We tried cutting the spring on the DPDT switch, but it just wasn't working as well, and the rubber band ended up being the best solution.
If you're interested, here are any of the references we used in the presentation. And thank you so much for listening, and we're opening to any questions.
Hold it closer. Thank you. Another really great pitch, and I thought your presentation had some really interesting theory discussion, which helped to understand why you'd gone for the option that you'd gone. So well done for that. When you're doing reactor design approvals, one of the things you put an awful lot of effort into is doing the opposite of what you've done, which is try to prove why it's a good design. We push the designers to tell us why it's a bad design. And what we're doing there is, what are the faults? What are the accidents? What can go wrong? What if that breaks? If that breaks, how do we still prove the design is safe? If that fails, how do we still prove that the design is safe? So we create these kind of layers of so what in what's called a fault sequence, and we develop that into big accident sequences. And every step of the way, you're trying to prove that the design still maintains the right margins of safety. Now, you're not designing a nuclear reactor, get that. I'm not going to put you on the spot there. But my question is, when you're designing, what hazards, what faults and failures were you trying to guard against? What do you think the most likely sources of error and failure were for your concept, and how does your design against that?
Well, I mean, I think we mentioned one of them, which ended up being the rubber band for the DPDT switch. We knew for a fact that if that did not activate, it wouldn't go back to the actual, it wouldn't reverse. So that was one of the main things that we really insisted on. We tried lots of different rubber bands, how to set it up, how many loops we had to do on it. We then also tried to modify the DPDT switch itself, like the actual spring on it, to like reduce it. And we ended up doing the rubber band because we clicked it, I don't know, we clicked it so many times, really different ways, different angles, different pressures, different speeds on the car, and it ended up working every single time we did. And there was also the normally closed switch. When it comes back, it's gonna hit it. We also discovered that once the car actually goes off, the closed switch will not come back all the way. So we then sanded it down slightly just so it wouldn't hit the edges anymore, and now it comes back oftentimes.
And also, just to add to that, initially our car was going much faster than we had planned for it to go, which was causing a completely different issue with the DPDT switch because we had too much force on it. So then we added resistors which slowed it down to our target speed, and that's when we realized we need to add the rubber band because otherwise we weren't having enough force for it to properly click each time.
First of all, great presentation, guys. My question is, after your first wheels broke, what was your considerations in the second wheel design to ensure that it could withstand the forces?
Thank you for the question. Sorry, should I go back to the? Yeah. So as you can see, the central bit where it's joining, that would just fully crack. And our main consideration was just making the whole center thicker. So on Fusion, we just basically made a bigger circle around the center just to make sure it's thick enough. But yeah, that was also one of our main considerations where things could go wrong, as mentioned in the first question, which is why we went through different iterations and we tested it with different materials.
Okay, thank you very much for your presentation. 3 things for me. First, can you confirm your year?
We are first year.
Fantastic, thank you. Then, pretty much Matt has asked the same question in a different team. I haven't seen great evidence of different design for the position of the axle. So now you're front-wheel driving, if you want to talk in a car world. I haven't seen that you have investigated rear-wheel driving, or instead of this latching mechanism, another one. So we haven't seen evidence of why you cherry-pick this design compared to the other one, like a scoring matrix or anything like that. That was one of the things that we kind of would like to see, your journey before you start to cut stuff. And second, I understand what you said about the 3D printing versus other stuff, or gears versus pulleys, but I would like to have a better clarification. Why do you think the 3D printed gear is less robust than a pulley? Because in a pulley, if you don't have the tension of the band, it will not deliver torque. So the load that you apply in a pulley to deliver a lot of torque is actually higher. That is the reason why in high-end transmission, you get away from pulleys and you get into gears. So the reality is that if you do a good design, a gear is always more robust than a pulley. It may be more expensive, but that is a second thing. So could you please expand a little bit on this?
Yeah. So with the gears, the reason we decided to go with a pulley is we actually used a toothed belt in the end to make sure that. Can you see the teeth in that? Yeah. So to make sure, as you said, that there's no slippage between the belt and the pulley. Yeah, that basically eliminated any error there with slippage.
And then for the tension that you had mentioned, I'm going to go right here. We added little sliders right here on our motor, so we could push it all the way, and then we're making sure that the belt has lots of tension. And then going back again on the first initial question, we had tried different positions of the motor, and we had realized that thanks to the design of the teeth, we could have it slightly less tense, and we would still get, and we would film it in slow-mo, and they wouldn't skip a tooth. They would still stick together. Ended up working really well.
And just a final brief comment on that is that when we were 3D printing it, because our first gear was so small, if we had 3D printed them and used a proper gear system, they would just, inaccuracies in the printer would just interfere with each other and potentially cause it to jam or stop, and we decided to not risk it and use a pulley system because that had proved to be it was working each time.
I think it's also worth mentioning that because our measurement system happens along the axle itself and not in the actual pulley system, even if it did slip, it wouldn't make a difference in the accuracy of our vehicle stopping.
Thank you very much. One question that hasn't been asked, and I noticed in most of the designs, the form factor of the chassis and the wheelbase, it's most of them kind of square. Yours appears to be the same. Have you explored other configurations, wide and short, or long and narrow, or any other wheels placement or configurations?
So something in particular we're looking for is the adjustment mechanism for the whole vehicle. That's why we used rather long width for the car, so as to align it properly on the target.
And you were talking about the dimensions of it. So we made it as long as possible, so that distance traveled was as short as possible. And then going back on what Pablo said, which was the axles themselves. Can you guys try to find a picture of the entire, at the beginning? Oh, there you go. Perfect. So exactly. So the axles we didn't shave them down. We kept them the original length. And since they're 300 millimeters, if there was a slight issue with them being aligned, right or left, the issue would be less significant because they're that wide. If they were shorter, that error would be more significant, would be more seen in the actual runs.
Okay, thank you very much, all teams that came here to present, and congratulations. I would like now to move on for the design review. Okay, so I will call each team, the top 3 teams to come, and we're going to project your CAD models here. And the questions are going to be led by Captain Matt Lister. Okay, so can I please have here UCLA?
Yeah. We had an actual fusion.
Yep.
Right click here. Sorry.
Yeah, let's do that. Shall we go and get it? Want to go and get it? Thanks. Yeah. So hopefully everybody's familiar with where we're at. So there was a pre-scoring done, which is why we've got the top 3 pre-scored teams. So I think we're now going to grab hold of the physical model itself. I'm going to give you guys a chance to talk me through how your physical model aligns with your CAD model. And then I think we're going to do a few dimensional and weight checks. Have I got that right?
Yeah.
Okay, great. Over to you.
Okay, so you want to bring it in center, Leo? So we did the CAD before we built the actual car, and everything we did in real life was based off of the CAD. Initially, in order to build an accurate CAD, we started by building a prototype base out of plywood. We were able to then drill this plywood base and see what we need to adjust before building in those adjustments into CAD before creating the final base. You will notice, are we allowed to move the CAD around? Or no. You'll notice that every single mounting point has an adjustment slot, such as the front axle or the motor's mounting. This allows us to mitigate the impact of manufacturing tolerances and make sure that everything still works fine. It's unfortunate that we don't have the actual fusion file, but all our weights are modeled in CAD. So we looked at the center of mass, we looked at the actual center of the car when positioning, say, the start switch. We put it right center to make sure that it doesn't move the car when you start it.
So with regards to the physical material, so you know, in the render you can add material, and inside the CAD you can add the physical material as well, and it will have the property of the material, so it makes the CAD more accurate to the car itself. And obviously it's not going to be one-to-one in terms of the numbers in CAD and the numbers that we get in real life, but so most of these parts are 3D printed, so they're pretty accurate in terms of properties, dimensions. So we did 3D print in the slow for the Ultimaker Cure. It's the 0.6 millimeter setting, so it's the slowest it goes, so the more accurate it goes. So it's accurate to 0.6 millimeters. And for these wheels, they were printed using a Bamboo Lab 3D printer, and these were using Ultimaker 2 Plus Connect. So that's pretty accurate and it replicates that, but obviously the properties aren't going to be pinpoint perfect because that's just the nature of how things is. But lastly, and this, I talked about the acrylic base plate already, but that's laser cut, so that's pretty perfect as well. So in terms of these parts and not the bought parts, the ones we actually manufacture ourselves, we try to make them as accurate as possible, so it's replicated throughout the physical model and the CAD.
So really enjoyed this model. You know, the level of accuracy and detail in it is really top notch. The fasteners look fantastic. One of the things I really liked about this that I thought was a bit distinct, if you flip it over, We've got the detail of electrical wiring. So you've got not just electrical components and the battery, you've got the detail of where it comes in, how that works its way through the back of the chassis and through to the top. You know, so that's a real standout for me in terms of the level of detail that we're seeing in the CAD model. I think if you wouldn't mind, just could you show that to the judges? Just give the judges a chance to have a bit of an up-close look. Of course, yeah.
I'm just interested. I appreciate you've put an adjustment in. Now, without the adjustment, when you were cutting this, you had precision. You knew exactly where it was going to go. You've introduced a slider. Where is your precision, and how are you measuring, how are you making sure that error is within, because that's not the way you do it on a vehicle normally.
So the slider, as I said, allows us to adjust for manufacturing tolerances. We used big calipers to measure the distance in between axles and to make sure that they are parallel. But moving forward, what we would like to do is use a small lead screw that would allow us to precisely move the axle forwards and back and actually record how far back and forwards it is.
Yeah.
So that would be the final way of doing it, and we have plans for that for the future.
Yes, thank you.
Yeah.
Just to add to that, whilst you're absolutely right, with the plywood base plate we had exact positioning, but we also have to take into consideration there are several other components in the powertrain. So not to mention like the wheels as well. These wheels, yes, they're 3D printed, but we've also drilled through them and we made adjustments to the wheels. So there's that kind of manufacturing tolerances once we've made the acrylic base plate. Yes, we know exactly where it was when we made the plywood base plate, but we need to make those changes in the future, and to allow for that, we have the slots and the acrylic base plate. So I hope that makes sense.
Yes, I'll explain. Okay. Would you mind just walking that down so the other judges can have a nice up-close look at your model? Is that okay?
No, the car.
The car, yeah, okay.
Yeah.
Thank you. So, as echoing what Matt said, it's great accuracy in the CAD. One question and one reflection. One, what did you learn by being so accurate in CAD when it was time to build it and test it? And the second one, which how can I say, as a basic, as a foundation, I disagree with the concept of the adjustment, and I'll try to make it even stronger. So the brief of this project is to go from A to B and coming back to A within a precision. Why do you think it would be better for the product to add the stuff? So if you have something that does the job, what is the benefit of adding stuff? So I'm the customer, I want to see the product that does the job, potentially within the best cost possible, within the highest simplicity possible, so that if I want to buy it, I know that you will be able to build a lot of them in the time given. If you start adding stuff just to do the same job, what is the benefit you give to the customer? So when you think about the design, think about, do I need to add something or not? Yeah. So the example of the adjustment that you want to have, that could be a gauge that you use to build your device, but you don't have to build it in the device.
Mm-hmm. That is true. So I think in a final version, we would like to have precise holes, maybe with no adjustment. I guess the benefit of adjustment is that it lets the vehicle cope with various terrains or surfaces.
So why would you think to add the stuff?
Yeah. So another benefit of...
One adjustment would have been sufficient. So if you have one axle which is fixed, and you just move one of the other one to make it straight, that would be sufficient.
The rear axle is fixed.
And you could adjust only on one corner of the front instead of everything.
Yeah, so if you... the rear, if I...
So you have two adjustments. One of them is to adjust the straightness of the axle, and one of them is just to tension the belt. If you had mounting precisely, you couldn't get the belt on. So one side is to get the belt on, and then you move it to the furthest forward position, and then you leave it there. That's not for adjustment, while the other side is for adjustment.
Great. So which design would have not had the issue of the tension of the belt as a vehicle?
Either a two-wheel drive design or one that uses gears.
That was that was the thing that we would like to see. Which pros and cons do you got in the design that you may have analyzed and potentially show, look, this has this benefit, I'm very precise, I have this, however, this is the downside of it?
Yes, we have tested this same car with two belts, with one belt and with no belt, and we noticed that with no belt it was slightly worse, and there was no difference between the use of one belt and two belts. And since we had a cost cap, we decided to just put one belt, but it would have worked slightly worse with no belt. So that's our, it wasn't really design process, it was more like throughout testing.
I'd also like to mention that we used the CAD and all of the adjustment to allow for precision in our kinematic model. So we modeled the cars and all of the forces, including the gear for the meshing forces between the gears and the drive torque coming out of the motor, and the resulting friction, to model the movement of the car as accurately as possible. So including four-wheel drive, we can actually ascertain the fact that there's only 4 milliseconds of slip at any point on the driving and on the reverse direction. And that's partly, in fact, because of the fact that we outsourced the worm gear at the rear, which has outsourced the manufacturing of that for higher precision in manufacturing and lower tolerances. And as a result, we are able to essentially verify that the design choices we've made here were both modeled well, and then when we tested it in real life, it performs to the same degree.
Okay, thank you, team. Judges, have you seen enough bloodshed? Any more grilling required? Okay, I told you superheroes face their moments of peril. You're about to face yours. I invite you to weigh your device, and can you show me on your CAD model what the mass you're expecting this to be is?
There were some issues when exporting the step file, especially to get the required AP Tier 3 file. So for some reason, our weight doesn't match our fusion weight when we export in step.
Okay.
But it does match the bomb weight.
What's the bomb weight?
862 grams. 862 grams.
Okay. Have you just read that off the scale? No, no, good. All right, okay.
What's the weight here?
It's wrong.
What have we got, Davide? 838. That's very close.
Is it?
Okay, it's very close, yes.
It was hard to model the motor and the battery in CAD, so yeah, that's probably where the imprecision came from.
That's why in the BOM, I mean, we weighted each separate component. We weighted each separate component, and that's why the BOM has a higher precision weight than the CAD, because we weighted each of them.
I'm going to give you a term here, margin. Okay, engineers work to margins, not exact targets. Okay, it's the same in nuclear reactors, submarines. You have margins, you have tolerance margins. So the fact that it's not exactly on a specific gram number shouldn't cause alarm. Okay, what we're looking for is obviously the closer it is, the better. And the closer you're into the margin, the more money you can save your customer, because you can give them that margin back, and that can be recycled back into the capability. Okay. So don't feel like you've got to defend it overly, but we've got a good reading on the scale, and we'll double check that away from the carpet floor, just in case that's giving something away. Any final points for this team? Judges, are you satisfied? I think we move on. Let's say next team, please. Thank you.
Can we have here team UCLB, please?
Ooh, sorry. I say this to my children all the time. Where's the car? We need the car. Oh, good, thank you. Right, okay, so you get to drive this. We've got a really impressive CAD model up in front of us. You know, there's an awful lot of detail here, and it was fabulous to see in the pre-scoring. I give you a chance to throw the pitch open. How does it align to your actual physical model? The same thing again, we'll give the judges a bit of a chance if you can make sure that they get a chance to look at that up close, and then we'll have the moment of truth on the scales.
For the accuracy of the CAD, one of the things we did was for every individual component on the car, we would pull up the actual specifications from the website and individually model each component separately. I don't know if you can see on the side, they're all modeled separately, which allowed for, if we had any changes, for them to be like immediately done in the CAD. You can also see the wiring underneath. But it means that each of our components is dimensionally accurate and accurate to the actual specifications on the website where we purchase the components.
You'll see on the underside of our car the wiring that we ended up doing. It matches pretty well. Really well, actually, I believe. Thank you. Thank you so much. And we also added cable ties, which are also located on the car and in the CAD model, which is nice. I don't know what else to say.
So go on, I'll fill the moment of silence. Again, this is a really, really impressive CAD model. We've got the fasteners, we've got the fixing. There's a lovely level of additional detail. You've even got the battery brand right, so congrats on that. We've got a good representation of electrical components right down to the sort of cablings and the cabling fixings, which is good. I think in terms of visualizing the item, you might change colors. I note that your colors are slightly in and off, but was it? Right, okay. It's an artistic flair thing. I shouldn't worry about it. What weight should we have here? What's the mass you're expecting?
800 grams from memory. I think from memory 800 grams. Yeah.
So close. Is that inside a margin for you guys? Do you feel that's inside what you were expecting? And what sort of error sources do you think you get in terms of mass?
On the CAD, especially the motor is probably one of the heaviest components, and we had some issues with the actual specifications of the motor being not very accurate on the website, which wasn't very helpful. So I think that's probably going to be one of the sources of errors, given the actual mass of the motor is quite significant.
But I think the most accurate things that we can say were the 3D printed pieces. On the slicing software, before we put it on the 3D printer, we got a mass estimate, and then we checked that. And that was, we couldn't tell the difference between them both.
No, that's great. So we will give you a chance to do this with the other teams over on the desk shortly. Judges, anything you'd like to ask?
Yes, we do also have slots.
How did you set it up in Calibre?
Oh, I can answer that. So there were two things. First off, we wanted to make sure that, actually, can you hold it? We wanted to make sure that when we actually align the motor and add tension to it, that it has to be tense. We've got the sliders for those. But then there's also the two axles that have to work together are the top ones, because there's a guide rod at the top, and then there's the actual axle. So those also have sliders. And the way we did it was that we fastened the threaded rod that acts as our driving axle, and we let the other axle unfastened, and we let it do the entire distance, and we let it kind of calibrate it itself, because it has to go, they're connected through here. So they have to be perfectly parallel. So instead of doing it by hand, we ended up letting it go, and then we fastened them. And then with lots of runs, if we would know automatically if they weren't parallel to each other, we could quickly fix that. And then after doing lots of runs, we decided to just move slightly each time the axles until we got it right on.
No, I get that, but I can assure you when I take my car in for an MOT, they don't keep running up and down the road.
Right. That's fair enough, yeah.
Anything else from judges? Oh, we got a question.
Just a question. I saw that you interpreted, or somehow one of the things that we didn't write in the rules, it was asking the student to think about. You interpreted quite well how to control the end flow of the shaft, so you bought some very inexpensive component, the star locks, to push them on and control that activity. So I was almost aiming to get the student to find that solution that is inexpensive and very precise. And then you bonded onto some plywood, some rubber band, which is all going all over the shop. Did you not have any reserve to instead 3D print a wheel with a nice groove and put an O-ring so that your rubber band may have not contributed to any, weird movement maybe moving forward?
So we do have rubber bands on it, as on the CAD, but we will probably run it without them, because we did so many tests with lots of different rubber bands that at the end, without the rubber bands, ended up being better, just the flat surface, if I'm going to be completely honest. And yeah.
We did initially consider putting rubber bands on the inside of the wheel just to attach on the axle to increase the friction, but after we'd cut it and printed it, we just realized that having a really tight friction fit, it was going to work just as well, and the rubber bands could, there was just more room for error there.
The comment I was making, we see somebody else has used a commercial O-ring with a nice groove to work as a bicycle tire, so that you don't need to worry about the misalignment, gluing it or whatever, and you know that it's always going to deliver a very good friction. So you will see somebody else having explored that idea and use it. But anyway, very good cut, very good execution. Thank you.
There's one more question.
Thank you, David. That's great. Excellent. I really enjoyed that. Thank you very much indeed. One of the things that you pointed out yourself is that it's quite difficult for the bill of material, for the motor to be accurately represented in CAD because the brochure numbers perhaps weren't spot on. Did you recognize this at a relatively early stage? And did that influence in any way the positioning of the battery so as you got some sort of center of gravity down the longitudinal axis? I'm concerned that if you've got relatively low friction tires or relatively low friction wheels, and I think you had a too high speed problem at the start before you put in resistors, whether in fact any offset of the center of gravity would have disturbed the tracking of the machine when you hit the wall. Was this considered?
So the motor originally we made before the motor in the CAD was made when we originally created the bill of materials before the components were bought. But considering the dimensions, they're as accurate as we could possibly make them when we received the component. But there were still slight issues with the specifications. But when we received the component, we did testing to ensure that the actual motor we received was as accurate as possible to make sure that the center of gravity was effective for the car.
Right, thank you.
Thank you, UCLB. Can we have here Imperial steel shafters?
The first thing you'll notice is there's no colors in the CAD because we exported it as a step file from SolidWorks. So the step file didn't contain colors. You can see our poster here is a colored version. So it was really important to us that everything was modeled extremely accurately to the real life component. So we had an initial CAD model from the specification online, and then we went back with calipers and checked all of the dimensions. The car should weigh 518.4 grams. Okay, that's not bad. So a big thing for us was manufacturing tolerances. So the main two manufacturing methods used were 3D printing and laser cutting. So we printed and cut first laser cutting. We cut a square piece with 3 different 8mm holes, and one was 7.95, one was 8mm, and one was 8.05mm. And then we went back with calipers and measured these to ensure that the tolerances with the laser cutter were going to be acceptable. So the laser cutter, we found, always cut oversized, and the 3D printer would always print oversized. So we could then account for this when we manufactured the parts. As the mouse is working. So the other thing was these limit switches. We made sure to model them as accurately as possible. I don't know if I can hide this. Using the data sheet. Because you can see our limit switch is fit with some set screws. And with the initial model we had, the basic model, which was just a square, we were finding that it didn't perfectly fit. So we went back, remodeled the limit switch with the dimensions measured in real life, and it was a much better fit. And it generally meant that everything fit, perfect friction fit first time round. Where's that part? Unhide it. Yeah. Any? Yeah, you can take it.
Also, another thing to keep our CAD always up to date was that because we were 3D printing and laser cutting everything, every single design change, no matter how minor, was first made in the CAD because, I mean, it just had to be necessarily. So that meant throughout the whole process, we never the CAD always represented whatever prototype we had at the time, which made it really good when then we came to the end of the process. There wasn't much to do. So, yeah.
You mean the pulley? Yes, you can, yeah. Can you show? We made the motor, you can move it back and forth to change the tension in the pulley with this, yeah. Small.
Yeah, any questions?
So again, a really nice model, and there's an exceptional level of accuracy here. You can see each of the individual fasteners shown, and there's an awful lot of detail on the components. Again, it passes the sort of litmus test for me in terms of we've got detail of all the electrical components, including the wiring, showing how it's moving in between. So that really helps to visualize and understand what the concept is doing. I like the fact that your component naming and nomenclature aligns with what's in your BOM. It makes it really easy to understand and see the accuracy in there. 2 degrees off weight, how do you count for that? Probably 2 grams rather, sorry. I think that battery's not fully charged, whereas I think that one is fully charged. Is probably the distance. Okay. Judges, questions? Oh, we got one at the back.
No, it's a beautiful model. Thank you very much for letting us look at it. It's very, very nice indeed. The bearings, are they little ball bearings that I can see in the hubs?
Yeah. They're the most standard ball bearing size, so they're very, very widely available, inexpensive bearings. And they were press fit inside the hubs. They were press fit inside the hubs. We 3D printed 3 blocks with 21.95, 22, and 22.05 millimeter holes, and see which was the best fit. And we found that the exact 22 millimeter outer diameter was a good friction fit.
Right. I can't see any trimming adjustments for tracking at all, but
we've got one
I
on here,
missed that.
sorry, yeah.
Oh right, okay. Yes, I can see it now. Yeah.
And it's only on one wheel of one axle, because adjusting that one wheel accounts for steering the whole car. I'll hide one of the O-rings so you can see the profile of the...
And yeah, also to talk about the wheels. Oh.
Hi, I wanted to ask, how do you attach your wheels to the axle?
So they're actually the wheels are O-rings that are 48mm outer diameter, and the wheels are actually sized to fit an O-ring of 52mm outer diameter. So you can just pop one of the O-rings off and see that they're just a friction fit, and the tensions are they're in tension. So what do you mean? The axial? Yeah, we've got set screws in on the shafts, which we don't seem to have here.
Are they threaded through the plastic?
Oh yeah, so actually that's a good point. Or we have no nuts on any of the parts because they're all printed out of nylon, which is a fine material to tap. We also ensured that when the wheels were printed, nylon warps quite a lot when it's 3D printed. So to mitigate that, the wheels are printed with the key axis, the key part of the wheel, which is the face of the wheel, printed first, which has the least warping, and then as the axis rises on the 3D printer, the hub becomes slightly less accurate and warps. But we found that we used a Mark Force printer with very high precision, and there were no issues with tolerance there.
Thank you.
So we've been talking with all of these about the functionality and the tolerances and the science and what have you. At what point in this project do you feel that aesthetics, how the thing looked, felt, entered into any of your design work, or didn't?
Very close to the end. If you see on our table, there are some prototypes, and they were a complete mess. Like we're talking like blue tacked breadboards to around like a square piece of acrylic, like batteries hanging off, like dragging behind. Like it was very, very late on. We decided, like once we had a design that we knew consistently worked, the circuit worked, because that was the most important bit. We then were like, okay, then can we take off material? Where can we make it look? I mean, here's a car, part of our car. Literally, that's all scrap acrylic, which is why it's got sparkly wheels. Like that's just what we could find at our workshop and stuff. So, like we were literally in the workshop for hours. Like we would find an issue, laser cut a new part, super glue it on. Like, oh, that works great. And then in the last couple of weeks, like since we've broken up, we've then eventually finalized it essentially and produced this final design.
So does form follow function or function follow form?
Function for sure. So that's what I tried to add. We made sure to optimize everything in our designs for practical functionality. We believe aesthetics come with it, and particularly with manufacturing. So one example would be the PCB. Of course, it's ultimately for ease of manufacturing, low cost, and functionality. It's 1,000 times more reliable than breadboard. But that means we can also print some cool things on there, like we have our team name on the team logo. And thing is, once we have the functionality and design sorted, we could rearrange them to make them fit in a nice, flush way so it looks symmetrical. For example, all our cutout holes were made sure to look nice. They don't have to be like that. They could be better, but we thought, for such a small compromise, why not make it look better? Because we can. But definitely functionality first, and then we make it look good, both with what we have.
Thank you.
So as everybody has mentioned, a very, very good execution, a very good alignment between CAD, and the CAD is very detailed. You did a very good job. If I don't give you a bad point, then I will not be happy. So I need to be happy first.
Thank you.
So you did everything was managed, was there. You didn't include in your laser cutting cable management. So if I look at your prototype and your CAD, the cable are just hanging off. There is no space for a zip tie or other holes, like your colleague previously have done, creating some little holes to clip them. Just a small suggestion. The other one is that all that piece, the electronic board that you designed, has some electrical component exposed. Even if you have put conformal coating afterwards, it would be nice if you put a little bit of tape on top of them before we do the actual race.
Okay, yeah, we can do that. Yeah. All right. And for the wiring, we initially planned to super glue the wires to the bottom here, as it's shown routed in the CAD. But yeah, no, that was not a good idea. Made it difficult to swap components, and yeah, in the future, we're definitely going to think about adding some cable management to sort of make it cleaner.
With your design, it will be just nice if you just put a couple of eyelets and you pass your wire in and out.
Yeah.
Then you don't even have to add the components onto it. So think about that one. It was nice to see from young students such a good and accurate execution. Thank you.
Great, thanks.
Okay, judges, have you wrung enough out? Are we good? Okay, many thanks.
Okay, so this is the end of the design review for today. We are running a little bit ahead of our schedule, which is good, no problem. So I would say let's stretch our legs, now for a little bit. And then lunch is going to be served soon for everyone. And then during lunch break, as I said, we'll be doing the scrutinizing of the devices and also the peer review. Okay, thank you very much for all teams for their presentations and answering the questions. I know it's not hard. It's not easy, sorry. It's not hard. It's very hard. Yes, thank you very much.
I'm going to go and get a coffee though. Can I get you a coffee?
Is that direct to microphone? That's RF receiver. Yeah, but the microphone. On the other one, not directional. Right, okay, thank you.
Is that staying away from my hands underneath? Can you see that? Okay, that's camera 2. That's lane 2. Tell me if you can see it now. programming, can you reset those?
I've always wanted to get into mechanical engineering. I love the fact that it's very broad. LSBU has supported me from the very beginning with regular employability sessions available. They also provide regular training on a variety of different softwares based upon what industry you want to go into. The facilities here are very wide ranged. So we have things like state-of-the-art 3D printing labs, as well as a variety of well-stocked metal workshops and wood workshops. I'm very excited to get into industry. I'm able to go into a variety of different fields and really make an impact wherever I go.
Right, let's go.
Okay, I'm here with Connor, one of the team members of the Middlesex team. How you doing, Connor?
I'm not doing very bad. You know, I'm just excited to be here.
Excellent. So, just before we start, I should let you all know watching at home that this is essentially what this is a stencil for the judges to determine how large the devices are. So we've seen all sorts of sizes in devices, and this has been the easiest way of measuring just to make sure it's within tolerance. Now, Con, I do have a few questions. So how did you find the design process today?
The overall design process for designing my device, it was a bit challenging. I'm not gonna lie. When I did design my device, we did try to streamline the design, just try and make everything a little bit smaller, because we was worried about the overall dimensions. But we decided to just more or less use our original design because we just felt that it was more stable, more secure, and just more or less housed everything better.
Excellent. And at the moment, are there any design changes you'd want to make?
Some of the overall design changes, now that we know the overall layout of our design, is try and reduce the amount of materials that we have, try and find a way to overall just clean up all the wires, making sure everything's in a nice, secure position. I would definitely like to try and see if I can use less wheels, like 3 wheels. I know I can't use 2 because then it would just be a motorbike, and that's not really a good way to drive a thing straight. But yeah, those are some of the changes I'd like to make.
Excellent. And just so I've seen your design. It's an excellent design, by the way. What would you say played in your favor in terms of features you've used in your design?
That is a good question. Some of the features I'd more or less say is the overall tendency, just like taking a look at everything and just stepping back and going, right, what if this was to happen? Like the overall design process from when we were first designing our device was just more or less checking, right, we've done this, but what happens if, this happens with this? What happens if a wire gets caught in the cogs? What happens if, the wheel stops turning in the back? And with that, it just more or less led to more sensible decisions, because originally we was going to use 2 motors, we was going to use this whole different gear system. But then when we took it into a more practical aspect and actually thought about it as designers and as engineers, it just became a situation of going, right, do we actually need that within our device? Because we do have a budget of £40, which is not really that much to work with, but overall there is a lot of stuff that we did do to basically go, right, is this the best for us?
Okay, excellent. I suppose one thing that you did do quite well was there was a recyclable requirement, and I believe you did meet that because a lot of your frame seems to be made out of wood.
Yeah.
Is there any other reasons aside recyclability that you chose wood?
Well, the reason why we chose wood was because it was more or less the most stable and structurally sound material that we had currently available at the time. Like, we did have acrylic available to us, but when we did notice, using the acrylic, we did notice it kind of flex a lot. And we were just thinking if we added more weight on it, it would flex more, the device could move left or right. Overall, it wasn't really practical for us to use it, so we decided to just more or less go with 4mm PDF board. And we more or less used our previous rigs that we made into supporting our actual overall design, whether it be just carrying up the original pieces and laying it on top to secure the wheels in a straight position, or if it was just using it to put something here and there. But yeah, no, with the recyclability of it, I think it's very important, especially in this day and age.
Agreed. And one of my final questions would be, so having now attended and competed as part of this design challenge, for those watching at home who may be interested in attending or even contributing to one of the future challenges, is there any advice you'd want to give them?
The real advice I'd just more like to give is just go for it. Like, when I first came to uni, I thought, about this competition, I thought, I'm not going to compete. Like, that's being plain and honest and truthful. Because I always thought that, this design's not going to really work well. I thought, this could go wrong or this could go wrong. But the overall experience of me just learning, okay, I've got to do this or I've got to do that, it was more or less a real eye-opener for me as a designer, because it just allowed me to go, right, my idea can work, but it can still be improved upon. Because I'm not going to make something perfectly within my first year. I'm not going to make, the next big brand new car. I'm not going to make the next, toy available. I understand that, my product and my ride right now is not the best. But I do understand to get it to at this point is some sort of achievement, which I honestly believe that every person out there who's watching this can, get to this point.
Thank you very much, Connor. It's been it's been a great experience interviewing you. Thank you so much.
Thank you so much.
Cheers. Thank you. Okay, guys, thank you very much for being back with us. I'm here with Alvaro, one of the team members of the Kingston team. So for those of you who've just joined us, I'm Abdul. We've got Alvaro, and essentially, I'm just going to get right to it. Basically, Alvaro, it's a pleasure having you here with us today.
Thank you, Sam.
Thank you. Just a few questions. So, currently, at the moment, with everything you've seen here today, are there any things you change about your design?
So, well, especially now after talking with the judges that just came by our stand, I would say we would try to reduce a bit more the cost of the device. Apart from that, I think we are pretty happy with the job we did. We try to do our best, but obviously the competition here is incredible. All these teams are incredible. So yeah, probably reducing a bit the cost and maybe just try to tweak certain small things. Maybe improve a little bit the design of the chassis. Maybe give it a bit more flair. But yeah, apart from that, we're quite happy. Yeah.
Excellent, excellent. So I'll give you some time to answer this one. But what would you say would be unique about your design?
That's a very good question. I would say, well, the main feature that distinguishes us is, I believe, that we try to recycle as much as we could of the main material, which is the MDF. So our suspension parts are all made out of the leftover material from the MDF, the big MDF board that we had.
Yes.
So I would say that probably the recycling, everything is made out of MDF, and then apart from the axles made from just bought off the shelf, the rest is all MDF. So I would say that probably that's the main feature maybe that can distinguish us.
Excellent, excellent. So there is a very heavy recyclability influence on your project.
Yeah.
That's great. That's great. So essentially, my next question would then be, in terms of like time/ease of manufacturing, how long did your product take to make from start to finish?
So, well, we went through different prototyping stages. So we made 5 prototypes. This is the last one. If you, like now, for example, our last prototype that we have with the design and everything, we could get it in, like we can assemble it within the day. Like within the day we have, you just wiring, soldering. If you have all the parts, you can do it in a couple of hours.
Yeah.
Obviously, it was a very long process, so we went through different iterations of the prototype. But this final product, if anyone would have to just make it all over, or we have to make it all over, we could just do it within a couple of hours.
Excellent. That's excellent. I suppose that brings me on to one of my last questions. Essentially, so as you've said, there's been a very heavy recyclability influence. What else influenced the design?
So we, at the beginning, at the early stages of the project back in September, when we were briefed about it, we took inspiration of previous year's competitions from like 2021, I believe it was, when they did the repeatable vehicle, the same challenge that we are doing this year. We went through all the recordings from previous years. We went to speak with also teams at our university that went through the same. We actually like a couple of designs from UCL winners in 2021, and then we had other alternatives coming from different other inspirations, but the main one I would say that's the 2021 IMechE challenge. We went through it. We skimmed through all the video, all the different, even for poster presentation, just to make sure that we were online with everything.
Excellent. And now that brings me on to my last question. So we always love to encourage people to join the competition. What would be your top 3 tips for anyone who's looking to join the competition?
Top 3 tips. I would say, well, you need patience, mainly, especially on group projects. You know, things can get difficult at times. You know, also, you know, when you are going through your course, it can get rough at times. Just go with it. Patience, communication with your team, especially I think communication and having a good vibe with your team, super important. And then enjoy the process. The beginning, when we were briefed about this project, we were like, oh, where are we going to start? But just, you know, take your time, do your research, and then just go with the flow. And yeah, I would say just enjoy the process. We learn so much.
I personally, I cannot believe that I am at this point now with all what I learned about engineering design, about electronics. If you were telling me this in September I was like, oh my God, what are we gonna do, you know? So yeah, enjoy the process, and then yeah, communication with your team, have a good vibe with your team.
That's excellent. Thank you very much, Alvaro.
Thank you very much.
For agreeing to be interviewed with us. Now, stay tuned, folks, because we're going to be having plenty of other teams here to do interviews with us. So don't go too far. Thank you.
Thank you.
I've always wanted to get into mechanical engineering. I love the fact that it's very broad. LSBU has supported me from the very beginning with regular employability sessions available. They also provide regular training on a variety of different softwares based upon what industry you want to go into. The facilities here are very wide ranged. So we have things like state-of-the-art 3D printing labs, as well as a variety of well-stocked metal workshops and wood workshops. I'm very excited to get into industry. I'm able to go into a variety of different fields and really make an impact wherever I go.
Right, I'm here with Victor from the LSBU team. Essentially, Victor's part of a team called Team Chariot. Do you care to tell us why that is?
Yeah. Actually, the name is Rebel Chariot. Yeah, basically, our device has some legs at the front. We've been inspired by Theo Jensen. He's a designer and engineer as well. And he set up the ratios for the legs that we made, and we finished them in our own way.
Excellent, excellent. So obviously this is LSBU, this is our home team, so I'm very excited to interview you. So out of the 11 teams here, where do you think you stack up compared to the other teams?
Well, it depends. There's 3 prizes. To be honest, in the design prize, I think we are above the rest, just because we're different. But when it comes to precision, I don't think we are on top.
And what would you do differently now that you've seen the competition?
Well, talking about my model?
Yes, your model specifically.
The thing is, we were lacking of time, and also we had an Easter break, and our colleagues, they were on holidays and that. So, to be honest, with more time, I think we could make a better device.
And what would you say is like the, besides the inspiration, what would you say is the best thing about your model?
Well, it's visually attractive. That's what everyone likes. I mean, if you show my device to someone that doesn't know about engineering, what is going to look is at the look of the device. So how it moves and everything, you'll see later, is like, it's cool.
Excellent, excellent. And in terms of manufacturing, you use, I believe, laser cutting.
Yeah, we laser cut some pieces in MDF, 6mm MDF. And also we 3D printed also a lot of pieces.
That's excellent. And also, I suppose it would just be, in terms of current testing, so what you've tested with, how do you think your odds fare in the races, which are the next portion? So just to let you know, everyone, so currently we've been doing the peer review section, the session. So essentially what that is was they were going around and essentially just, sort of like scrutinizing one another's model. How did you find that process, by the way?
Can you repeat the question, please?
So the peer review section, how did you find that in terms of like going around and having to actually look at every single model and look for the details, essentially?
Well, I think it's necessary because we're scoring our models, and a fair way to score it is to go to the other models and ask yourself questions, because then you can be tricky.
Excellent. And I suppose one of the final questions would probably be, so now that you've competed as part of this design challenge, what advice would you give to anyone else who'd actually want to try something like this?
Well, as an engineer, you try and fail. So try as much as you can, try to find the error, and just solve it, because that's why we're engineers.
Excellent. Thank you very much, Victor.
Thank you.
And just before I sign off at the moment. So we have races coming up. So of all the 11 teams, each one of these teams will be racing between the short range, the medium range, and the long range races. So we'll pan over to the racing area, and I'll be there to give you commentary. So stay tuned for that. Thank you very much.
Thank you.
Thank you.
They said the tape, like, I assume they'll just move it every time. Like, you can tell that some of the cars like fucking run the ball like a rocket. Like, that's gonna bounce. 100%. I think it was the LSBU one. I think the one in the end. I don't know. Oh, it was brick. It was brick actually. You're right. thanks, man. You too, man. Good presentation. I want to see some more electronics, and like, there are some like slight advantages, but DPT people are really fine. That's just pretty cool. I want to do some more PCB design and do some stuff like that. And they're better for than now. So it gave us a lot to talk about in the presentation. So.
Yeah, that's usually right.
And one of the judges came over and was like, oh, I was hoping someone would use logic gates. Yes. But I think one of the other teams has got like a full binary counter. But like, I was like, there's no way that's 100% makes sense. Because just like, we were going to do a binary counter. You'd have to have an optical encoder, which is like a sensor. We asked IMechE, okay, we asked for some clarification as to what sensor is, because a button's a sensor. Yeah, that's what I mean. We asked for clarification, and just like, don't risk it, guys. Like, it's not worth wasting all that time on it and then getting there and being told that's actually not allowed.
Wait, I just realized they're gonna like do 4 runs simultaneously. Like they will change the holes. So those who are here and there are fucked.
Yeah, you switch in between the lanes. You do one of those lanes. Yeah. No, I think because why are there 4 lanes and 3 distances there? It's pretty cool. If we don't switch lanes, it's a bit bullshit. Come on, man.
Nah.
It's not like no range. This one's fine.
Yeah, this one's fine. If you do 4 meters there, then you're dead. Yeah. Like, the whole competition is a joke. You know what's funny? If you look on the project specifically, essentially on the PDF is not structured. So they print it off the website.
Okay, ladies and gentlemen, so now the moment we've all been waiting for, the races are about to start. Each one of the 11 teams here will have the opportunity to race between the short, medium and long range. I'll be providing commentary throughout the races, and let's get ready to start.
Yes. Come back. Wow. 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 Just make sure that the pictures shows that it works. Oh, you lost it. Really? This is the back. I'm not nervous. This is your starting round. Yeah, you're starting round. We did everything. So is it a double 10? Yeah. Supporting me.
That's a good one. Well done. It's more about the alignment. If you look at the procedure, well done.
Okay, ladies and gentlemen, we've just finished the first round of races. We've had the UCL team A and Team B, as well as the Imperial College London team, the Team Steel Shaft. So far, so good. The races have been very, very close. And stand by, because we're here to give you more updates as the next round of teams get ready to race.
Do you want us to give a hand when they're ready? Everybody ready? Not ready here yet.
You ready? Yeah. Get your needle. Okay, yeah, we're ready.
Hands, everyone? Yeah? Okay, 3, 2, 1, go.
Millimeter up. Oh, wow. Almost. Let's go forward.
Okay, ladies and gentlemen, so we've just had our next round of races, and so far, UCL Team B seems to be doing extremely well. Both rounds they've ended up in the white for the bullseye, and honestly, it's very exciting stuff. They also have they seem to be the team with the most amount of speed as well. So we will see, and it seems to be playing out in their favor. So stay tuned, as the other teams are almost about to end, which is, oh, so UCL Team A also extremely close. There's very exciting races going on. So stay tuned for our next round of races. There'll be one more switch. So each team currently now has done a short range and possibly a medium range. But essentially what's happening is they're rotating. So stay tuned, and we'll be back with more commentary. Thank you.
Okay, when you're ready, just show me your hands, please.
Not ready.
Okay. 3, 2, 1, go. Okay, great. 1 minute commentary.
It's not on the boundary, it's in yellow. It must be the same as the camera. That's the thing. Gives room for error. You short off. I'll say
UCLA.
Okay, ladies and gentlemen, so we've just wrapped up the first round of races for the short, medium, and long-range distance races. What seems to be common is that as the longer the race is, the more likely any inaccuracies will be made more obvious, essentially. So we will be having more teams come through. So at the moment, we just wrapped up with UCL Team A, B, and Imperial College's team, known as the Steel Shafters. And yeah, so just stay tuned, and we should have more content for you coming soon. Thank you.
Show your hands, yeah? Everyone? Okay, 3, 2, 1, go.
You can't touch it. Pull that back. You can't touch it
Ladies and gentlemen, back again at the races. So we've currently had an LSBU team as well as two Middlesex teams. So one of the Middlesex teams, known as Team Brick, did very well. So a lot of speed off the get-go, very close, in fact, to the bullseye. It was an excellent race. The other Middlesex team did, in fact, a little bit better in the mid-range tests. Very promising results. They're just setting up now for the alternative races. Unfortunately, though, the home team, LSBU, took some very bold design changes, including legs in their designs. Unfortunately, this did backfire this time round. However, I believe there will be resetting for the mid-range tests. Unfortunately, at the end there with the LSBU team, the legs did fall off, but with the reset and a much shorter distance race, I feel like they'll be really good. There's a lot of promise here, and they have taken a great risk in including this design change with the legs. Hopefully, it'll pay off. Stay tuned, folks. Signing off for now. Thank you.
Why did it break down?
Okay, we're going to stop you guys there for this particular race, okay? So we've got 2 teams left competing in this one. Whenever you're ready.
Okay. Yeah. Hands up, yeah? Right. 3, 2, 1, go.
Okay, ladies and gentlemen, so now after another round of races, we've got some very exciting commentary now. Essentially what's happened is, unfortunately, due to mechanical failures, Team LSBU, well, a single team from LSBU was given around roughly 2 to 3 minutes to essentially try and attempt to repair those mechanical failures, but unfortunately we didn't make the mark on that one. So we weren't able to race on that one, but they are allowed to reset and then, you know, try a final attempt at the short distance race, which they have done so. So this will be the final chance, essentially, to try and get a successful lap in. One of the Middlesex teams, Team Brick, unfortunately did also experience some losses. Essentially, what happened is that the racer or the device essentially hit the wall, but unfortunately didn't activate the reversal switch, so it was stuck at the wall. They have been given the opportunity to continue with the medium distance race, and the Middlesex Team A seems to be successful in all 3 races, but we will find out in this race, which is the final race for Middlesex, the other Middlesex team. So far so good, but stay tuned, and hopefully we can get a much more interesting race in this one. High hopes. But yeah, stay tuned, folks. This is really exciting.
Risk assessment. It's not. I don't know if the tape will stick. Is it set properly or is it all the switches to the TT? Well, at least for everyone to see. I mean, it reached
Okay, teams, that's setup time complete. So, you ready or not? We're about maybe might work on the steps.
3, 2, 1, go.
I think maybe we could lose it to the wrong place. Guys, can we have a round of applause for LSBU?
Okay, next team. Team Stone.
Okay, ladies and gentlemen, so we just finished one of the round of races. Essentially, we had a team from LSBU, we had two teams from Middlesex. So the team from Middlesex, known as Team Brick, unfortunately, on the long distance race, their device did not return. However, they did have good success in the medium distance race. Essentially, they missed the bullseye by a bit, It did shift a little bit to, I believe, the right, but unfortunately we did experience a complete catastrophic failure with the Team LSBU. But you know, it was an excellent attempt, and they were commended for it. But yeah, stay tuned, folks. Middlesex Team A though did do exceptionally well, so I believe in that leg of the race they were the top team there. So stay tuned. We've got plenty more exciting races to come. Thank you.
allowed 2 minutes. Are we okay? Because they need to reset their motor. So is it done? Okay, you just you can touch it now. What did you got then? Oh, you didn't go? We start a 3-minute clock. So now we can move around. Yeah, move around. Move around. Move around. Yeah, yeah. With your... Thank you.
Okay, ladies and gentlemen, so do not count out Team LSBU. They have just pulled off a shocking sort of run. So out of the three teams currently on track, Team LSBU, Team 2 on Team LSBU, essentially managed to is the only team that actually managed to complete a run on this session of races. Unfortunately, the 2 Kingston teams were experiencing some technical difficulties, but there is going to be a reset, and they are going to be allowed to essentially recalibrate and recoup. But this is a great win for Team LSBU. Stay tuned, folks, because the races are really heating up. Thank you.
Just waiting for them, I think. We're still in time. Yeah.
That's what all that's for. Are they counting up? Yeah, it's just I can nudge it over if you want. Wow. Yeah, it's just
and no friction.
put it on the paper. Just stand there now.
So it was you disqualified the team.
Are you ready, teams?
Okay, ladies and gentlemen, so just to set the scene, essentially what's just happened, we've had the previous team, the previous set of races essentially was just concluded. It was very, almost heart-stopping essentially. The suspense in the room was very, was there. The suspense was honestly very intense, and that just concluded the first leg. So essentially what's happening now is, what's going to happen is that we're going to have the last two teams here racing. Once that happens, we'll be finishing the first round of races. After this, there'll be a second one with another set of teams racing. But essentially what's just happened is Team No Friction has taken the win from Team UEL in the first set of races. They will alternate between medium and short distance race, but at the moment it's looking very good for Team No Friction. Stay tuned, folks. The suspense is a lot.
You have 1 minute left. Great. Three, two, one, go.
Right, folks, we're back for the final race of the first leg of races. Team UEL and Team No Friction from Imperial College London. So far, we've seen plenty of exciting moments, and honestly, many that have left us speechless. Targets they tend to be landing in the bullseye very, very often. The accuracy is very difficult to tell because on the long distance races, any errors tend to be more obvious, and the shorter distance races tend to be less obvious. So this is the final set. This is the final chance for both teams, essentially, to go up against each other, essentially. And honestly, this is a lot. The atmosphere is completely quiet, and just stay tuned, folks, because this is the last bit of the first round. Signing off for now.
Okay. 3, 2, 1, go. Okay.
Right, ladies and gentlemen, we've just finished the first leg of races. Currently, the judges are deliberating to see who will go into the finals of the races. It's been very, very suspenseful. It's been very exciting. Although the races are quite slow and there was a lot of silence, you could tell the suspense was definitely there. So I'll be talking with Ben.
I thought the tension was hugely exciting. What was your favourite moment so far?
Favorite moment 100% was the team LSBU, watching them. So I feel like when you're watching like your home team, there's a lot more suspense. So I was literally, I think I was standing at one point, I was on my knees on the other point, and I was looking away. It was so many emotions in one, purely just terrifying.
How do you think Team LSBU are feeling about things right now?
Probably a lot worse than me, but I'm not sure of their confidence levels. I do think they've done enough to do to make themselves proud, essentially. So I'm proud of them. I'm sure they're proud of themselves as well. But yeah, overall, I'm proud of the university. But there is a lot of fierce competition today, so we'll see how that goes for them.
I've seen various devices that just consistently finish within a millimeter of the target. Has that been a kind of mood of today, that there are some unbeatable teams here?
To be fair, I had that assumption at first, but there's always that element of you never know what can happen, so you just plan for the worst. So we did have quite a few times where a few teams seemed very good in the first few portions of the race, but then in the other races the device either wouldn't turn on or they missed the mark when with the recuperating time, which was about 2 minutes. So as you can see, there's still races going on. I believe they've repaired some of the faults they had. That's actually Team LSBU in the back there.
That is Team LSBU, and one of my favourite things that happens at these events is when teams do running repairs, head off to the workshop, fix something, and then come back and have it working again. I have a feeling it's going to be too late for Team LSBU, but I'm delighted that they're out there with a successful device. I've seen a little bit of human error today as well, people pushing a button that then doesn't actually push and doesn't work. Is the human side as important as the design side, do you think?
I believe the aim of this whole thing has been to sort of try and reduce the human element to it, in the sense that you want the machine to be doing most of the work, but with repairs, especially doing a repair within 3 minutes, a lot can go wrong. So that currently, I think a lot of the teams have done well, but in the times where you've had to have that human intervention, it's not always the best option. But the spirit of the race is really what counts.
If you were competing in this competition next year, what would you have learned from this year for it?
I would have learned that ideally try and go for something that works, but always remember to bring that LSBU flair. But I think overall, it's one of those exciting moments, and I think we just stay tuned. And I believe the judges are about to deliberate and give us that final verdict.
Brilliant. Something that works with LSBU flair. That's what we're going for. Thank you.
Excellent.
Oh, you beautiful little boy, you. Come on. Don't die. Yeah! Oh, now it's gonna go off the track. It's got stage fright, that's what I'm telling you. It's not the legs were when there's a just needed rest and a little bit more time. We can. Please tell me fun. Yes.
Okay, Victor, so we've just seen you racing. Can you explain what just happened?
Yeah, the device, I mean, one of the joints snapped, so yeah, we couldn't continue the race. The thing is, we fixed it afterwards, after the competition, and now it worked, so we're able to show you.
Excellent, and it was an excellent device whilst it was working. We just want to thank you, for really representing that LSBU spirit and culture of never giving up. What exactly went wrong?
Well, actually, this is called Theo Jensen's mechanism. It transforms circular movement into triangular movement. So just to give you an idea, it tracks the device. It has too much tension in the joints. The joints are a bit fragile, and they are 3D printed, so it's not the best. So yeah, I think they were under stress, and because of that, they snapped.
Thank you very much, Victor, for that demonstration as well. And thank you for representing us. It was a pleasure being here. Thank you.
Because there's only 3 tracks, they only do it. But there's 14, so one is okay.
That's just the distance.
Okay, ladies and gentlemen, so I'm here with Connor. Do you care to introduce your team?
So my name is Connor Warnes. I'm joined with my partner Rainier. We're from the Middlesex Design Department. I'm a first year student and this is my device.
Do you mind walking us through the device and how it works, basically?
Oh yeah, I can easily walk through it. So what we have here is a Google Gear system. So a Google Gear system is basically a system of gears that's used to basically slow down one main gear from like 100 RPM all the way down to 1 by just more or less making sure that the driven gear, the gear that's going to be driven, has more teeth than the driving gear. So what we were able to do is just more or less reduce the amount of spin from this wheel all the way down to here to around about 3. Now, when we did test this out, we was doing very well, you know, it was getting like 2 millimeters, 3 millimeters away from the center. However, when we did...
we have a 4-way tie after these. So we're now going to move on to the final event.
A 4-way tie, you heard it here, folks. It's a 4-way tie. We're just waiting for now at the moment.
UCLB, no friction, and steel shaft. There are 4 finalists in compete again with you guys, and we'll get to them.
Well, you heard it here first, folks. A 4-way tie. So we're going to have a final, and essentially they're going to do a tiebreaker, and from there the judges should have enough information to give out the prizes, essentially. But continue on with this interview. Connor, please tell us one more thing. Essentially, how do you think you did in this race, and what would you change?
To be truthful, I think I did fairly well. You know, I'm proud to the point of where I've got to, you know, competing in regionals, you know, being in this position where I'm actually competing. Obviously, you know, I'm a little bit upset that I didn't win, but obviously this is a great learning opportunity for me to actually be here. So if I was to do this again, what I'd more or less do is just change the overall gears, change the motor to a much more slower motor, and just overall improve the device's shape. But yeah.
Excellent. Thank you very much, ladies and gentlemen. So we're continuing on with the rest of the races. This is the final, and stay tuned and we'll have more information for you soon. Thank you.
Too far. Too far.
On the X.
Ready, teams?
Wait 1 second.
Okay.
Yeah, I have 2 minutes. Okay. 3, 2, 1, go.
Okay, move round 1 lane, please.
Okay, ladies and gentlemen, so we've just finished the first set of races in the finals. Not completely though; they are changing. So they'll be switching lanes, changing from between short, medium, and long distance. UCL Team A essentially seems to have been doing extremely well in the medium length, hitting the bullseye on this one. UCL Team B was doing the long distance race. Again, that one does make any errors more obvious, but it was very, very close, and they did, although they didn't hit the bullseye completely on the mark, they weren't too shy. Team No Friction from Imperial College London doing the short distance race, they came up really accurate as well, and now we're just going on to the next portion of these races. As you can see on the screens, the teams have switched between lanes. Stay tuned, folks. This is getting really, really exciting. Thank you.
touchy, yeah?
Okay, stop.
Okay, if you're ready, change lanes, round and clockwise.
Ready? Just wait until the other tracks on. Okay. 3, 2, 1, go.
That's good, Victor.
Yes!
So we've just got steel shafters to go. So these three teams, thank you. You can retire. Steel shafters to the road track.
Right, ladies and gentlemen, we just finished the run with UCL Team A, B, and the Imperial College team, Team No Friction. It was very, very close. I believe there was some human error with Team No Friction. Unfortunately, that did mean that, you know, they may have been penalized for one of the races. UCL Team A and Team B, very close, but there was a lot of excitement coming from UCL Team A, so fingers crossed for that. At the moment, it now just rests on the final race. Team Steel Shaft, and I believe this should be the last team. If they take this one home, then it'll be, you know, it'll be the end of team. I believe it will mean that Team UCLA will be in second, but we'll have to wait for the judges to confirm that. Stay tuned, folks, because this is the most exciting part of the race. So don't miss it. Thank you.
Maybe I can. Do you have it?
Right, ladies and gentlemen, so we've just finished the last race of the second leg of races. So it was a lot of suspense. At the moment, the judges are in the deliberating room coming up with a decision, so we should have a final winner shortly. Elisa, how do you think the races went today?
I think it was brilliant. I think all the devices were, all the efforts that the students put into the devices. We got some brilliant design here, great engineering, and let's just take into account that most of them are first years. Being a first-year engineering student is tough. And I think all the effort they put is it's amazing. It's a great also addition for their CV to be here and participate on this event and competing, doing networking with the other team. So great experience.
Excellent. So we're just going to cut for a moment and we'll be back shortly with a final decision. Thank you very much for joining us today, but don't go too far.
Thank you.
Exactly now, like these 3 days.
Yeah. It's so funny to see. What is UC? Oh, that's because you have different receiving guys.
Yeah. The main one, not the Yeah. Because they've got one in Boston, very big, and they've got another one, but I don't know where it is. 360. Maybe. Yeah, they got Max Space in King's Cross, yeah. The switches I initially set up. How is it there? I like it. It's a massive sit down.
I have always wanted to get into civil engineering because I've always been fascinated about the makeup of buildings and infrastructure and how they're made and the different parts that go into making an actual building. So this year I was nominated and won the Women in Property Regional Awards. It's been an amazing experience. I've managed to grow my network and gain a lot of experience within the industry. We have access to a wide range of facilities, one being the materials lab, where we get to visualize how materials behave. So over the summer, I did an internship with a structural engineering consultancy. It's been amazing being able to put my theoretical knowledge into real life practice. I have always wanted to get into civil engineering because I've always been fascinated about the makeup of buildings and infrastructure and how they're made and the different parts that go into making an actual building. So this year I was nominated and won the Women in Property Regional Awards. It's been an amazing experience. I've managed to grow my network and gain a lot of experience within the industry. We have access to a wide range of facilities, one being the materials lab, where we get to visualize how materials behave. So over the summer I did an internship with a structural engineering consultancy. It's been amazing being able to put my theoretical knowledge into real life practice.
Yeah. Oh, that's not glued on properly at all.
If it was a smaller piece, it's like this. Yeah.
Should we rip it off?
I mean, yes.
I mean, you don't need it anymore. Just you want to rip off the front?
Yeah, let me just try it like this, because I put it a bit of...
See how straight it is?
Yeah, I put it alcohol free. No, I put it in purpose. It's alcohol free.
But still, it's way
Because I actually like it.
I think really.
It tastes like beer, but at least it doesn't.
It does taste like beer. It's still on the right.
Oh, they got the proper one.
Look the line.
It's on the line.
Yeah,
it's
on the line.
It works.
It's not on the tuck, it's on the line.
Do you want to remove the beam? Do you?
Yeah.
I mean, we don't need any of it anymore. We're just playing around with it.
Wait, I gotta film it. It might be worse.
But the worst already happened.
Yeah.
Yeah, you were so unlucky because if you started there instead of the 4 meter one, you would have got
probably some.
Yeah.
Is it straight?
Probably the most inventive one.
Let's go. It is the coolest one here. Oh, is it? Does it go straight? No. Let's see how it is coming back without the thing. I mean, at the angle it was going, I think it's slightly better.
You need the right down the bowling alleys.
Yeah.
Keep me fluid, wait. Wait.
Yeah, I'm waiting.
Got on us.
You want me to wait completely straight?
Yeah.
Okay. I think it is. Ready? It's not going that hard. Yeah, now it's a bit off. But it's because one of the joints is fucked.
I think it made it worse actually.
No, it's struggling.
Oh, is the joints gone out?
It's gonna snap. No, wait. It's gonna snap soon.
You reckon it's retiring now?
Yeah.
It lasted for a little bit.
You wanna listen the shorter one? Let's go the shorter one. Let's do.
Well, I'm getting it worse.
Thanks for that helmet thing display as well.
I'm glad you had the opportunity to show it working to everyone.
That's too.
No one took the risk of going like yours.
Thank you.
Exactly.
This is the shortest one?
Yeah. I'm hither.
No, you can't go around in the face of everybody else in the class.
This mistake will show here.
Oh, now it's way up. Yeah. Is it dragging? I think maybe it's retired. Yeah, we gotta curve it this week. Oh, wait. Wait, Victor. Let's curve it. Come back, boy. Come back. Hey, it's better. That's on the line. That's pretty close.
It's just I couldn't see it.
That was straight.
Come back. Oh! It got on the target!
Why can you recreate? What did you change?
Nothing.
Well, we took the stem off the front, and at the starting position, we got it on like an offset, so it like curved back into the middle.
That's what you see. Even yesterday. Started curves into it.
But you know the one they had before this one that had compound legs.
Oh, I had 8 legs.
This is the coolest one here. Like this is easily the coolest vehicle here.
Let me show you the other one.
This is pretty boring. The coolest one.
Bro, is that gonna go? Is it gonna? Okay. Is it gonna go on the line?
We're using the same motor again.
Yeah, we are actually. Yesterday we tested it, and every single time it went off the track.
Look at this.
Oh my god, that was so fast.
Yeah, do you see those flecks?
That was our like.
Why did you change it from that one? That one seems to be.
We had a lot of group communication issues, so we needed to.
Was a bigger group before?
We needed to find something that was possible to build.
No, it wasn't a bigger group. It was like two separate groups.
We had like 5 different groups throughout this whole process.
We were a tutorial group. We were together from day one. Actually, yeah, we did the.
Me,
This is extracurricular.
it was that so me and Victor, the other guy's not here, we were in separate groups, and Kristen only joined when it was just me and Victor. Because he was working on something else, the distance tracking was completely unrelated. And then he was told that would be good.
I was working on the challenge, but not
But all by yourself?
I didn't have a team. I wasn't able to participate. I just
And we didn't even know you were doing it. It's really very cool. Yeah. You see how we done it? And a lot of blue.
All necessary engineering components. All the best cars that I've taken.
Imagine that initially they were supposed to do one with 8 legs. So you saw those compound legs. Like 4 in front, 4 back, and then. But then, well, of course, you know, the initial idea was like shooting very far, but then they had issues with the group, so.
I think it's really quite good.
No,
it's like it's part of the TCD instead of like DVTD, so it's just so we can like try something different.
Yeah. There's so many reasons we can let me switch out.
Now I know more about PCB design and
there were so many
there
were so many ways to do this thing. So for example, this one has 4 switches for each one of the wheels.
Oh wow.
So and they are connected in parallel.
Yeah.
So and this one imagine that if you put for each voltage divider, you can actually have different speeds. For example, if you put on the first switch, it starts slow, then when it reaches the second wheel, it goes faster, and when it comes back and it reaches the first wheel, when it's almost to the target, it goes slow again. So you know you can actually have stages.
Very nice. No, that's interesting. That's very cool. See, there's 3 limit switch. Very nice. Limit switch party. Everyone's on DBTT limit switches. Yeah, exactly. Yeah.
There were a lot of options discussed with the guys. Due to the fact that they first year, the electronics skills,
we usually more. Yeah. Honestly, learning yourself is the best because you know exactly what you don't know the best. We have so many We were so doing from like 10 till 12. for like a week.
10 in the morning, 12 o'clock.
Yeah. My I just found you. I mean, I was
regular breaks. So no risk assessments.
So now it works, and it is want to do a demonstration for them.
Oh. You want to go?
I want to see this. You know, when you weren't here,
wait, try get it to curve again. Try get it to curve. I don't think it'll go straight.
So one version of this here is 36 degrees. Goes forward. Again, increment. One back. Again, opposite. Come back.
I mean, don't answer. There's no competition.
Initially, the higher ratio. So this every small tolerance, every small plane
times for one rotation of the shaft. Then the
Maybe we'll make an adjustment
because this wood, until this one makes a full rotation,
and then you can actually say, you can build a device that goes forward, comes back and tells you how long the wait was. Because that would be like user feedback, which makes it interactive.
That's the proof of concept.
Oh yeah, we had an overshooting problem when it came back in testing. Yeah. Okay. We would like rotate it a bit so it would travel less. So hopefully it would stop less. Oh yeah. Why did it have to snap? Why did it have to snap? I'm so upset. There's pins in here, guys, that joins this part. They're fixed.
I've got a friend who's watching this.
Oh yeah, what did he say?
She was like, holy moly, they got too dark.
Oh my god.
So you have admired, you see, not like people are watching it. Maybe about 20 people are and watching on the street. It's took 20 people to actually...
Kristen, let me video.
Just to take care.
I saw you around that camera. I said, ready? Oh my god! That was the wrong direction.
This is your fault.
Then we need to push back.
Julian, that's your fault. Because you said, let me film you. And it hurt you.
It's got stage fright.
Yeah, don't say it. Just do it.
That's what happened in the competition. It goes and it's not good. Maybe there's some points for enthusiasm.
Guys, you got the recognition in time.
That was a nice feeling. That was almost as similar to winning.
I think it's better.
Yeah.
I think it's better.
Is there a fan favorite category?
Well, you're my favorite.
A hidden category.
You're my favorite.
Oh, oh my god.
Well, I trained you, so you might. Right?
Oh.
She got 6 for it.
Come back to me. Cool. That's going to right. Huh.
A bit too much.
I feel like the adjustment, now we don't need to do the adjustment. I don't know why it's now working. It learns when it fails and gets hurt.
It's a mind of its own. It's AI.
Then we actually engineered a soul into this robot. It's alive and sentient.
It was not programmable. We did some voodoo shit. Yeah, he's Indian. He put some G inside.
Come back, boy.
So,
It did that consistently. It's being consistent.
This one really doesn't make mistakes.
Use a starting. It's more consistent now, Elisa. We only got it working first time.
Okay, good afternoon. We're finally there, the end of a very long day. I told you, superheroes, ordeals, long days, it goes with the territory. Before I get into the results, there's a few thank yous, and I think a round of applause due for some people who've really committed and put some positive vibes into this event. I'm going to start with Elisa and her team. An enormous thank you for your organising prowess. Out of sight, but not out of our hearts at the back, Alice and the team from IMechE, who facilitated the organising. Your judging panel, no booze, you haven't had the result yet. So to Charlie, Tom, Martin, Steve, and Davide, thank you. And finally, the various unnamed mentors, academic staff, supporters, helpers, friends, emotional crutches who've gotten you over the last 3 weeks, without whom these events do not happen. An enormous thank you to your friends. Okay, the results. So we've had a long day. It's been huge fun. Some of these conceptual designs we've had through and the work you've done on it absolutely blows away. The standard is really high. It is increasingly difficult to assess some of these categories. The competition itself, huge fun, good to see. I know some of you have tasted your first heartache, professional bitter heartache. It doesn't get any easier, I tell you that, you go on. But it's better to strive and to try than to never know what winning or losing feels like. So you've taken part, and good for you for doing it. But we have to have winners, and we're going to work through those now. So I'll give the second and third in each categories a round of applause for them, and then the winning team in each category, if you could come up, we're going to take the obligatory paparazzi photo for the web pages with some dummy prop certificates. Okay, first category is the poster category, and we had a joint second place for this, which was the team from UCLA and the Kingston University Team A. And our winning team for poster was UCLB. To the front, please. Okay, the next category, presentation. So third place, team UCLA. In second place, UCLB. And the winners of best presentation were steel shafters. Okay, the next category was the peer review. This was your votes. And in third place, we have the steel shafters. In second place, you have UCLB. And the winners of the peer review were UCLA. Okay, the next category was the marks for design, the CAD drawing, and the overall design concept. In third place was the team from Kingston University A. In second place was Steel Shafters. And the winner in the design category was UCLA. Okay, the last individual category is the challenge results, the timed events that we've been going through this afternoon. We have a joint second place, which was UCLB and the Steel Shafters. And in first place was UCLA. Okay, the final results. So this is the overall score and the winner of the event. So this is the team that goes through to Birdcage Walk. We have a joint second place. And if you could come up and take a final picture, we have a joint UCLB and Steel Shafters. And so, our overall event winners, the winners of the Design Challenge for Undergrad Edu-Engineers Championships for Greater London region, and our team that will be going through to the national final at the IMechE HQ is UCL Team A. I think we're due one more round of applause, and that's for all of the teams for taking part. It has been a fantastic challenge. As we said, the level of engineering work's been really high. We did have a concept team taking part today. They were the only team that took part, so they win by default, and that was the Des Eng team from Imperial. But as I said earlier, it's the taking part that really defines you as winners in this event. So a huge round of applause to all of you, and thank you very much.
Okay, so well done, all the teams. I hope you have enjoyed your day here at LSBU. That's the end of the foundation. We are going to have a second round tomorrow for the advanced challenge. We still have refreshments over there, so make yourself at home. And thank you very much for joining us today. Thank you.
Right, ladies and gentlemen, thank you very much for joining us today. As you heard it here, the overall winner for the foundation competition was Team UCLA. It was an excellent competition today, very exciting. And join us tomorrow. We've been very happy to host you all here. And tomorrow at 10 o'clock, we'll have the advanced competition, so stay tuned, folks. Thank you very much.